of extraterrestrial life? What are the origins and historical context of the Fermi paradox? How does the Drake equation estimate the potential number of technologically advanced civilizations in our Milky Way galaxy? In what manner does the Kardashev scale classify extraterrestrial civilizations? What is the Great Silence? Where are the signs from aliens? These are just a few of the mysteries we're unraveling in today's documentary. Let's go on a journey to explore these questions through a comprehensive scientific lens. When did humans first begin contemplating the possibility of extraterrestrial life? In ancient Greece and Rome, early thinkers like Democritus and Epicurus pondered the vastness of the cosmos and speculated about the existence of other worlds. They believed that the universe was made up of countless tiny atoms which randomly collided to form diverse worlds beyond our own. Epicurus's follower, Metrodorus, likened the idea of Earth being the only inhabited planet to expecting a single grain of wheat in an infinite field. Adding a poetic flourish to this philosophy, Roman poet Lucretius suggested that in the grand scheme of the universe, uniqueness was a rarity, implying the existence of numerous other Earth-like worlds bustling with life. While these ancient philosophers didn't conceive of stars as suns with planets like ours, they did imagine a universe teeming with diverse worlds. Their visionary ideas laid the groundwork for our modern fascination with extraterrestrial life, showcasing their forward-thinking perspectives on the cosmos. However, it's essential to note that their understanding differed from ours, as they viewed stars as fixed points on a celestial sphere rather than as distant suns with planetary systems like our own. In these times, thinkers envisioned other Earths as distant and isolated realms similar to today's concept of multiple universes, expansive, uncharted, and entirely separate from our own existence. However, as we transitioned into medieval times, the abstract musings of these early visionaries clashed with the more empirical views of Aristotelians who prioritized observable reality over imagination. Aristotle's immense influence led to the sidelining of the idea of many worlds. Nevertheless, this notion persisted, fueled by the tension between Aristotle's stance and the Church's belief in God's omnipotence. While the concept of many worlds remained dormant in philosophical discourse, it was ironically kept alive by the arguments used to discredit it, awaiting a resurgence. Medieval theologians emphasized that Aristotle's rejection of multiple worlds couldn't be treated as indisputable truth, leaving room for ongoing speculation within scholarly circles. In the 15th century, interest in extraterrestrial life was revived. Figures like Nicholas of Cusa proposed that life existed throughout the cosmos, extending beyond Earth. He posited that celestial beings created by God inhabited stars and planets of various ranks, offering a renewed perspective on the potential diversity of life beyond our world. Nicholas of Cusa proposed a fascinating idea. Beings inhabiting celestial bodies would likely differ from us, with those from sun-like planets potentially being more radiant and spiritual, contrasting with perhaps more diverse lunar beings, while earthly inhabitants might lean towards materiality. However, our understanding of these otherworldly beings remains limited, as we lack comparative standards. Unlike the Epicureans' notion of completely separate universes, Cusa envisioned a universe brimming with life, including various forms of beings on different celestial bodies, essentially what we now conceptualize as aliens. This concept sparked intense debate among medieval theologians, including Cusa's contemporaries, who grappled with profound questions. Did these beings experience a fall from grace akin to humans? Did they require redemption through Christ? French theologian William Vorilhon contributed to this discourse, suggesting that beings on other worlds were not burdened by Adam's original sin and thus lived free from its consequences. He proposed that Christ's sacrifice on earth held such profound power that it could extend across infinite worlds. However, he found it difficult to reconcile the idea of Christ suffering and dying multiple times on different worlds. Medieval scholars delved not only into the existence of inhabited worlds, but also into the theological implications, exploring how extraterrestrial life might intersect with Christian beliefs. They contemplated the cosmic role of humanity and the universal scope of Christ's salvation, weaving these concepts into the tapestry of their theological discourse. The prevailing notion that the Middle Ages were a dark era resistant to new ideas is challenged by evidence of medieval scholars engaging with the concept of extraterrestrial life. Surprisingly, this engagement didn't always lead to accusations of heresy or put lives at risk, hinting at a more complex intellectual environment than commonly assumed. During this period, curiosity about the universe and its potential inhabitants thrived, fostering debates and speculations about worlds beyond our own without immediate fear of condemnation. This challenges the stereotype of medieval scholars as closed-minded and stifling of innovation, revealing a more open and inquisitive scholarly culture. Nicholas of Cusa, for instance, was celebrated for his discussions on extraterrestrial life, earning him recognition as a cardinal and even a papal legate. Similarly, William Vorilong, who contributed to this discourse, faced no charges of heresy and was known for his opposition to the unjust trial of Joan of Arc, highlighting his commitment to justice and freedom of thought. These examples illustrate that the medieval period was intellectually diverse and less oppressive than commonly believed. In essence, ancient and medieval intellectuals were captivated by the idea of life beyond Earth. Early philosophers like the Greeks imagined separate worlds, while later medieval thinkers pondered the potential for other planets within our universe to host various forms of life. This intellectual journey represents a progression from abstract speculation to more concrete hypotheses about extraterrestrial existence, blending elements of philosophy, science, and theology. What are the origins and historical context of the Fermi paradox? Discussions surrounding the search for extraterrestrial life often center on two key concepts. The first is the Drake equation, a tool crafted by astronomer and SETI pioneer Frank Drake. This equation, backed by credible calculations, offers estimates reaching into the thousands of potential cosmic civilizations capable of emitting detectable signals. The second concept is the Fermi paradox, often misunderstood. It suggests that if intelligent aliens exist, their presence should be apparent through interstellar colonization. However, the absence of clear evidence on Earth raises doubts about the feasibility of detecting their signals. Interestingly, the Fermi paradox is incorrectly linked to physicist Enrico Fermi, who never actually proposed it. Despite its misattribution, this paradox has influenced debates on extraterrestrial intelligence and affected funding for related research. Senator William Proxmire, for instance, used it to argue for the discontinuation of NASA's SETI program in 1981. Though briefly revived due to advocacy from Carl Sagan, the program faced termination again in 1993 under Senator Richard Bryan. Despite the discovery of numerous exoplanets, federal funding for SETI initiatives in the United States has been lacking. Enrico Fermi himself, a Nobel laureate known for his contributions to nuclear physics, didn't leave behind any published works on extraterrestrial life. Our understanding of his views on the matter stems from accounts gathered by physicist Eric Jones from individuals present at a 1950 Los Alamos luncheon, Emil Konopinski, Edward Teller, and Herbert York, who outlived Fermi. The concept, often referred to as the Fermi paradox, traces back to an event where Herbert York and Edward Teller interpreted physicist Enrico Fermi's remarks as questioning the feasibility of interstellar travel rather than doubting the existence of extraterrestrial life. Thus, the term Fermi paradox, which implies skepticism about aliens, doesn't accurately reflect Fermi's stance. His skepticism about space travel aligned with the technological limitations of his time. Rocket technology in 1950 hadn't achieved orbital launch, let alone interstellar travel. The idea that the absence of extraterrestrials on Earth implies their non-existence wasn't initially proposed by Fermi, but by astronomer Michael Hart in 1975. Hart argued that intelligent aliens would inevitably colonize the Milky Way, and their absence here suggests humanity might be alone in the galaxy. This viewpoint, though criticized, has influenced discussions on extraterrestrial life. Physicist Frank Tipler expanded on Hart's thesis in 1980, addressing the resource requirements for galactic colonization. He proposed a self-replicating universal constructor capable of populating the entire galaxy. Tipler concluded that Earth's lack of such advanced technology implies humanity's uniqueness not only in the Milky Way, but in the entire universe. However, drawing such significant conclusions from the absence of encounters with extraterrestrial beings on Earth has faced challenges. Critiques include the possibility of unattainable interstellar travel, civilizations choosing not to colonize, or past alien visitations leaving no discernible traces. Despite these counter-arguments, Hart's and Tipler's hypotheses have left a mark on the discourse surrounding extraterrestrial life. The fundamental idea commonly known as the Fermi paradox is actually the result of the work of Hart and Tipler. Over time, their concept has become mistakenly associated with Fermi's initial inquiry. This confusion can be traced back to physicist David G. Stevenson, who in 1977 labeled it the Fermi paradox in a publication, suggesting Hart's theory as an answer to Fermi's question. A more precise term for this line of thought would be the Hart-Tipler argument against the existence of technological extraterrestrials. While this label might not carry the same historical weight as its misattributed counterpart, it would be a more accurate acknowledgement of its true originators. How does the Drake equation estimate the potential number of technologically advanced civilizations in our Milky Way galaxy? The core of this thought-provoking inquiry lies in the comparison between two profound possibilities: the existence of numerous extraterrestrial civilizations throughout our galaxy, or the solitary nature of humanity in the vastness of space. Consider the scale of the universe. It's teeming with an incomprehensible number of stars. Even within our own Milky Way, estimates range from 100 billion to 400 billion stars. And this is just one galaxy among countless others scattered across the cosmic expanse. Given this immense scale, the sheer quantity of stars suggests the tantalizing possibility that we are not alone, despite the potentially minuscule odds of intelligent life emerging. Frank Drake, a pioneering figure in this quest for understanding, sought to tackle this cosmic puzzle. He outlined a series of questions that scientists must address to estimate the number of detectable civilizations within our galaxy. By combining these questions through multiplication, Drake devised the now famous Drake equation, providing a framework for estimating the potential abundance of detectable civilizations. Within the intricate framework of the Drake equation, each symbol holds a key to understanding our cosmic potential. R* symbolizes the ongoing creation of stars in our galaxy, a celestial symphony unfolding annually. Moving forward, FP represents the fraction of these stars hosting planetary systems, setting the stage for the next question: which of these planets reside within the habitable zone? This crucial aspect of our cosmic puzzle is quantified by Ni, a value shrouded in the mysteries of extrasolar planets. While these worlds may offer potential habitats for life, the true extent of their habitability remains uncertain, a question addressed by FL in the enigmatic Drake equation. Phi sheds light on the number of habitable planets where intelligence has emerged. Frank Drake's gaze turned toward the realm of radio astronomy, envisioning his equation as a tool to gauge the likelihood of extraterrestrial civilizations communicating through detectable signals, an idea encapsulated by FC. In the 1960s, radio was widely seen as the preferred means of communication for advanced civilizations. Earth itself has been broadcasting a technological signal into space for nearly a century, potentially reaching out to neighboring stars within an 80 light-year radius, each one a potential listener to the whispers of life. However, a lingering question persists. Would advanced civilizations across the cosmos still communicate via radio waves, or might they consider such a method as outdated as smoke signals are to us? There's a possibility that some alien societies might intentionally conceal their presence from potential cosmic peers. In a diverse cosmos, it's conceivable that not all civilizations hold benevolent intentions, making the disclosure of one's cosmic whereabouts a risky proposition. The final variable in the Drake equation carries a weighty implication. It seeks to gauge the duration for which a technological civilization remains detectable. Represented by L. Frank Drake, harbored concerns that a highly advanced society might shine brightly, yet fleetingly, on the cosmic stage of observability. It's plausible that many civilizations, though they may endure for eons, could only be within our reach for a fleeting moment in their extensive histories. So what's the solution? When Drake initially formulated his estimates in 1961, he concluded that n, the number of detectable civilizations in our galaxy, likely ranged between 4 and 10. However, refining Drake's parameters with modern scientific insights paints a different picture. The revised calculation for n is a mere 0.00127, indicating that within any given 100,000-year period of our galaxy's existence, approximately 127 civilizations could emerge within the realm of detection. The foundation of Drake's work rested on the belief that extraterrestrial civilizations populate our galaxy. His calculations hinted at a rich tapestry of around 10,000 civilizations within the Milky Way alone. Despite the enormity of this figure, the sheer magnitude of the challenge in detecting even a single civilization among the galaxy's minimum of 100 billion stars underscores the immense task confronting astronomers. It suggests that a meticulous examination of 10 million stars is imperative before any skepticism regarding their prevalence can be warranted. In what manner does the Kardashev scale classify extraterrestrial civilizations? The observable universe, spanning over 13 billion years, presents a staggering expanse, housing approximately 2 trillion galaxies, each adorned with an estimated 20,000 billion stars. Within our Milky Way alone, scientists speculate the presence of around 40 billion Earth-like planets nestled within their stars' habitable zones. Such astronomical figures suggest that Earth may not be the sole cradle of life in the universe. The revelation of life elsewhere would revolutionize our cosmic outlook, revealing a vibrant cosmos teeming with existence. This realization could potentially elevate our collective consciousness, fostering unity in place of terrestrial discord. Yet, before embarking on the cosmic quest for potential interstellar companions or adversaries, we confront a fundamental quandary: defining the precise nature of what we seek in the universe's vast expanse. In a universe as expansive and ancient as ours, it's reasonable to assume that civilizations emerge over intervals spanning millions of years, evolving along diverse paths and at varying rates. This implies that our search encompasses not only vast distances reaching hundreds of thousands of light years, but also civilizations ranging from primitive to highly advanced. To refine our search for extraterrestrial life, we require a conceptual framework that aids us in thinking more effectively. Since humanity serves as our sole reference point, we must exercise caution when drawing conclusions based solely on our own experiences. However, certain insights can still be gleaned from our history. Humans, propelled by competition, the pursuit of resources, and a natural inclination for expansion, began their journey with basic tools and innate curiosity. These traits have played pivotal roles in the development of our civilization, driving significant advancements. It stands to reason then that extraterrestrial beings capable of dominating their own planets might exhibit similar characteristics. Furthermore, if these alien species are governed by the same physical laws as us, their technological progress could potentially be measured by their energy consumption. This perspective offers a potential metric for evaluating the advancement of extraterrestrial civilizations. Human progress, for instance, can be traced through our evolving ability to harness energy from our environment. Our journey commenced with the utilization of muscle power, evolved to mastery of fire, and further expanded to harnessing kinetic energy from natural sources like water and wind through mechanical means. With advancements in technology and material science, we progressed to tapping into the dense energy of fossil fuels. This escalation in energy utilization has paralleled our civilizational advancements. Expanding upon these insights, scientist Nikolai Kardashev introduced a system to classify civilizations based on their energy consumption, the Kardashev scale. This scale, although refined over time, primarily categorizes civilizations into 4 distinct levels. A Type 1. Civilization harnesses the energy of its home planet, while a Type 2 civilization extends its reach to harness the energy of its star and planetary system. Advancing further, a Type 3. Civilization exploits the energy resources of its entire galaxy and a Type 4 civilization transcends its energy usage to encompass multiple galaxies. Each level on this scale represents a significant leap in complexity and capability, akin to the difference between an ant colony and a human city. To an ant, the structures and systems of a human city would appear godlike in their sophistication. To make the Kardashev scale more practical, it's beneficial to incorporate subcategories for a more nuanced understanding of the vast disparities in civilization development. Within the Kardashev scale, civilizations ranging from Type 0 to Type 1 span a spectrum from primitive societies to those comparable to what we might achieve in a few centuries. Such civilizations could potentially be abundant within the Milky Way. However, the absence of active radio signal transmissions into space means that even civilizations in close proximity, such as those in the Alpha Centauri system, could remain undetected. Our own radio broadcasts, covering a radius of 200 light-years, are minuscule compared to the vastness of the Milky Way and degrade into indistinguishable noise after traveling just a few light-years. At present, humanity finds itself at approximately level 0.75 on the Kardashev scale. We've made significant alterations to our planet, constructing massive infrastructure, reshaping landscapes, and modifying the atmosphere's composition and temperature. If we manage to preserve Earth's habitability, there's potential for us to advance to a full Type 1 status within the next few centuries. Achieving this status signifies a natural progression toward venturing beyond Earth, driven by our inherent curiosity, competitive spirit, and expansionist tendencies. The transition to becoming a Type 2 civilization entails extensive forays into space. This journey might commence with the establishment of space outposts, evolving into the development of space-based infrastructure and industries, leading ultimately to the colonization and terraforming of other planets. As a civilization's activities and resource utilization expand, so too do its energy requirements. A pivotal milestone for an emerging Type 2 civilization would be the construction of a Dyson swarm encircling their star, providing nearly limitless energy for vast system-wide projects. With such capabilities, the aspirations of a Type 2 civilization would naturally extend to other star systems, reminiscent of our current perception of the distance to Pluto, challenging yet within reach with substantial effort and resources. This heralds the commencement of their journey toward becoming a Type 3 civilization. The challenges inherent at this stage are beyond our current comprehension, including traversing vast distances and maintaining coherence across light years, both culturally and biologically. It prompts questions about whether such a civilization could surmount the immense travel times, retain a unified identity across distant colonies, or if they might diverge into distinct civilizations or even separate species. The journey toward becoming a Type 3 civilization involves navigating not only physical distances, but also potential existential risks lurking in the interstellar void, as a civilization progresses toward Type 3. Status on the Kardashev scale, envisioning their form and nature becomes increasingly daunting. These civilizations might uncover novel principles of physics, master dark matter and energy, or even achieve faster-than-light travel. Their motives, technology, and actions could surpass human comprehension. In this context, we humans are akin to ants attempting to decipher the complexities of a galactic metropolis. To a highly advanced Type 2 civilization, humanity might appear too primitive for meaningful interaction, while a Type 3 civilization might regard us as we view bacteria on an anthill, possibly disregarding our consciousness or survival as inconsequential. In such a scenario, we can only hope for benevolence from these entities. However, the scale of civilization might extend even further. Some theorists speculate about the existence of Type 4 and Type 5 civilizations, wielding influence over galaxy clusters or superclusters spanning thousands of galaxies and trillions of stars. At the apex of this scale lies the hypothetical Type Omega civilization, capable of manipulating the entire universe and conceivably creating new universes. While speculative, this classification offers intriguing insights. If our assumptions about interstellar civilizations hold some truth, then the likelihood of Type 3 or higher civilizations existing near the Milky Way is exceedingly low. Their presence would be unmistakable, with clear signs of their activity spanning numerous star systems. Yet the absence of such evidence, such as harvested stars, decaying megastructures, or remnants of interstellar conflicts, suggests they do not exist nearby. This realization, although somewhat disheartening, also offers reassurance by suggesting that the galaxy remains open for humanity and civilizations akin to ours. The most probable extraterrestrial civilizations to discover would likely fall within the range of Type 1.5 to Type 2.5, advanced enough to be captivating yet not so advanced as to be beyond comprehension. These civilizations might be involved in constructing megastructures, voyaging between stars, and potentially transmitting vast amounts of information into space. However, it's conceivable that our comprehension of progress toward Type 2. Civilization is limited, and humanity's inclination toward outward expansion might reflect our current developmental stage. At present, our quest for extraterrestrial life is still in its early stages. Until we encounter advanced alien civilizations capable of unraveling the mysteries of the universe, we are left to our own devices in exploring the secrets of the cosmos. What is the Great Silence? Where are the signs from aliens? The haunting silence that greets our search for extraterrestrial life in a universe teeming with countless stars and planets is a perplexing phenomenon known as the Great Silence. It suggests a vast cosmos devoid of detectable signals or signs from alien civilizations, challenging our comprehension of the seemingly boundless expanse of space. In 1967, Jocelyn Bell, a postgraduate student at Cambridge University, was conducting sky surveys using a novel radio telescope when she stumbled upon a peculiar radio signal pulsing regularly every 1.33 seconds. Initially dismissed as human-made interference, further investigation revealed that the signal originated from deep space. Its consistent timing defied previous observations, sparking speculations about extraterrestrial origins. Humorously dubbed LGM-1, an acronym for Little Green Men, reflecting the initial excitement surrounding the possibility of alien communication, the mystery was soon dispelled as a natural phenomenon. The signal emanated from a pulsar, a rapidly spinning neutron star emitting radiation beams akin to the light beams of a lighthouse. Although this discovery debunked the alien theory, it catalyzed a global initiative known as the Search for Extraterrestrial Intelligence, SETI, aimed at detecting artificial transmissions from space. Despite extensive efforts, humanity has yet to discover definitive extraterrestrial signals. For about a century, we've unintentionally been sending radio signals into space, creating a radio bubble extending roughly 100 light-years from Earth. Within this range, extraterrestrial civilizations might be alerted to our presence. However, beyond this bubble, Earth's existence is virtually undetectable. Moreover, as technology advances, our unintentional radio emissions are diminishing, potentially leading to a future of radio silence. The fleeting lifespan of a civilization's radio signals in the cosmic timeline presents a challenge for interstellar communication. Additionally, these signals weaken as they traverse space. Military radar signals, being among the strongest leaks into space, have a higher chance of detection over vast distances compared to standard TV broadcasts. The upcoming Square Kilometre Array, a large interferometer in South Africa and Australia, may detect faint signals from Earth-like civilizations up to several hundred light-years away. Deliberate communication attempts, like the 1974 Arecibo message sent from Puerto Rico toward a distant star cluster, offer a more focused approach. However, these efforts are transitory, providing extraterrestrial observers with a limited window for detection. An example of a potential extraterrestrial signal is the 1977 WOW signal, a brief burst of energy that remains unexplained and hasn't been detected again. Ultimately, the chance of two civilizations coincidentally discovering each other by randomly broadcasting is slim. To enhance our prospects of contact, we need to refine our search strategies, concentrating on signs of technological and biological life in the cosmos. In 1995, astronomers achieved a groundbreaking milestone, the discovery of the first planet orbiting a star similar to our Sun outside our solar system. Subsequently, we've learned that most stars in our galaxy likely host at least one planet, with billions resembling Earth in size and orbiting within their star's habitable zone. This zone offers the potential for liquid water, a crucial ingredient for life as we understand it. Even moons orbiting these extrasolar planets might harbor life, with estimates suggesting there could be as many as 1 billion moons like this. Recognizing the potential for extraterrestrial life, in 2017, a deliberate message was sent to one of the most Earth-like exoplanets we've discovered, relatively close to us. This message contained musical compositions and information about humanity. If the planet is inhabited and capable of responding, we could potentially receive a reply by 2044. However, confirming whether a planet actually hosts life requires meticulous examinations, such as analyzing the chemical composition of its atmosphere. This is achieved by studying the starlight that passes through it. For instance, an atmosphere rich in oxygen, akin to Earth's, might imply the presence of life, as oxygen on our planet is largely generated by photosynthetic organisms. Nevertheless, the mere presence of oxygen isn't definitive evidence, as it can also arise from non-biological processes. Astrobiologists are particularly intrigued by specific combinations of chemicals that are unlikely to coexist without life, such as methane and carbon dioxide. Additionally, chemicals like carbon dioxide could indicate industrial activities and climate alterations, serving as potential indicators of intelligent life. Beyond these biosignatures, we may also detect technology-related cues known as technosignatures. For instance, an exoplanet adorned with a dense array of artificial satellites or space debris might be discernible when it passes in front of its star. Theoretical concepts like Dyson spheres, envisioned by physicist Freeman Dyson, represent another avenue of exploration. These speculative megastructures would be constructed by advanced civilizations to harness a star's energy. The Kardashev scale, proposed by astrophysicist Nikolai Kardashev, categorizes civilizations based on their energy usage. A Type 1 civilization utilizes its planet's energy, Type 2, its star's energy, and Type 3, the energy of an entire galaxy. While there's no confirmed evidence of Type 2 or 3 civilizations in the Milky Way, these concepts propel our quest for extraterrestrial intelligence. Occasionally, intriguing astronomical events ignite speculations about aliens. Take, for example, a distant star with erratic dimming patterns, which initially prompted theories about colossal alien structures obstructing its light. However, subsequent investigations suggest this phenomenon is likely due to dust, not extraterrestrial engineering. Despite such speculative musings, the pursuit of concrete evidence of extraterrestrial life persists. Particularly, astronomers remain fascinated by the hunt for life beyond our galaxy. Despite exhaustive surveys spanning 100,000 galaxies in search of signs of a Type 3 civilization capable of harnessing the energy of an entire galaxy, no traces of such an advanced society have surfaced. This profound cosmic silence raises significant questions, especially considering Earth's prolonged emission of detectable biosignatures for roughly 1 billion years, seemingly without attracting any discernible attention from alien beings. This disparity between the high likelihood of extraterrestrial life and the dearth of tangible evidence prompts what's known as the Fermi paradox. One plausible explanation is that life, especially intelligent life, is exceedingly rare. Earth's evolutionary journey, punctuated by numerous mass extinctions before the emergence of humans, lends credence to the rare Earth hypothesis. This hypothesis suggests that the development of complex life on our planet stemmed from a sequence of improbable events, potentially making Earth's life story a unique occurrence in the vastness of the universe. Speculations about the existence of a great filter, a formidable obstacle to life's evolution, abound. If this filter lies in the past, Earth may have successfully navigated it, rendering us among the fortunate few. Conversely, if it lies ahead, humanity could confront an existential threat that spells its demise. Another realm of conjecture centers on the nature of alien life. While life on Earth is carbon-based and thrives in water, extraterrestrial life might manifest in radically different forms, like silicon-based organisms dwelling in ammonia oceans. Such diversity could lead us to overlook signs of alien life because we're fixated on familiar terrestrial models. Moreover, there's the intriguing notion that advanced civilizations might transcend physical reality altogether. The transcension hypothesis, advanced by futurist John Smart, posits that such civilizations might retreat inward, engrossed in crafting hyper-realistic simulations and exploring virtual realms instead of the physical cosmos. Eventually, their technology could shrink to a scale akin to black holes, effectively rendering them invisible in the observable universe. In our quest for extraterrestrial intelligence, artificial transmissions and signs of astroengineering remain pivotal. Take, for instance, the iconic Voyager 1 and Voyager 2 missions launched in 1977, representing humanity's fervent outreach to potential extraterrestrial civilizations. These spacecraft, each bearing a golden record brimming with information about our species and the diversity of life on Earth, serve not only as cosmic explorers, but also as envoys, tasked with delivering messages to any extraterrestrial beings they may encounter. Voyager 1 embarks on a journey spanning 40,000 years, destined to traverse the interstellar void and approach another star system, while Voyager 2, taking a divergent route, has provided invaluable insights into the outer reaches of our solar system and ventured into interstellar space in 2018. As these probes traverse the cosmic expanse, they symbolize humanity's insatiable curiosity and our relentless quest to comprehend our cosmic abode, while their transmissions back to Earth enrich our understanding of the universe. Yet this technological prowess begets a confounding question. Why does our solar system seem devoid of such emissaries? Given the rapid pace of human technological advancement, one might expect the galaxy to be bustling with self-replicating automatons. Yet no tangible evidence supports this notion. Searches for alien artifacts within our solar system have yielded no confirmed discoveries, but the sheer vastness of space means that extraterrestrial objects could effortlessly evade detection. In 2017, an enigmatic visitor from beyond our solar borders dubbed Oumuamua stealthily traversed the inner reaches of our celestial neighborhood, eluding detection until its outbound trajectory from the Sun. Its serendipitous detection hinted at the possibility of numerous similar objects slipping past our surveillance. Oumuamua's peculiar morphology and anomalous behavior, initially categorized as a comet, then re-evaluated due to its absence of a cometary coma and unexpected acceleration, ignited debates regarding its nature, including conjectures of it being an interstellar probe potentially propelled by a light sail. However, Oumuamua remained obstinately radio silent, akin to a derelict probe aimlessly wandering the cosmos akin to Voyager. Our comprehension of life beyond Earth is circumscribed by our solitary example, our planet. The discovery of life elsewhere, even within our solar confines, such as beneath the icy crust of Europa, would furnish invaluable insights into the prevalence of life throughout the cosmos. The endeavor to unravel the mystery of the Great Silence has witnessed remarkable strides in recent years. The deployment of the James Webb Space Telescope in 2021 revolutionized the scrutiny of exoplanetary atmospheres, augmenting our capacity to detect potential signs of life. Initiatives like Breakthrough Listen have galvanized the search for extraterrestrial intelligence, employing more refined detection methodologies. The heightened scrutiny of Oumuamua-like interstellar interlopers has catalyzed discussions concerning their origins, whether artificial or if it was natural. The 2021 landing of the Perseverance rover on Mars marked a pivotal stride in the quest for biosignatures, deepening our comprehension of the potential for life within our solar neighborhood. Concurrently, astrobiology is delving into the viability of life in extreme environments, expanding the vistas of our pursuit of extraterrestrial life forms. These endeavors underscore an escalating dedication to unraveling the enigmas of the cosmos, recognizing the discovery of extraterrestrial life as an epochal milestone in human annals. Numerous scientists contest the notion of Earth as an unparalleled cosmic phenomenon, citing the abundance of Earth-like planets and life's resilience on our planet. Yet, the precise likelihood of life, particularly intelligent life, remains shrouded in uncertainty. The conditions requisite for abiogenesis, the transition from non-life to life, elude complete comprehension. Deeming ourselves solitary inhabitants of the universe lacks substantiation without further evidence. Our exploration for extraterrestrial intelligence remains circumscribed, akin to scouring for fish in a glass of water when juxtaposed with the vastness of the oceans. Space unfurls in boundless expanses, and our expedition has barely commenced. Multifarious unexplored avenues for detecting life await our scrutiny. By fine-tuning our telescopic apparatus, expanding their dimensions and tuning into divergent frequencies, we may unveil that the universe resonates with vitality far beyond our present discernment. What is the Great Filter hypothesis? Do we stand a chance at surviving? Space exploration stands as one of humanity's most extraordinary triumphs, with a plethora of exhilarating discoveries looming on the horizon. Yet, amidst this progress, a haunting query looms. Could our advancement be abruptly halted by an existential menace? The cosmos may eventually unveil a stark verity to humanity, the inescapable denouement that awaits all life forms. Enter the Great Filter theory, a speculative framework positing that every sentient civilization will confront seemingly insurmountable hurdles at some juncture, culminating in their inexorable decline, sans leaving enduring vestiges of their existence. Economist Robin Hanson introduced this hypothesis in 1996 as a plausible explanation for the Fermi paradox, the seeming incongruity between the high likelihood of extraterrestrial life and the paucity of substantiating evidence or interactions with such civilizations. Hansen postulated that the emergence of sentient life could be exceedingly rare, perhaps owing to enigmatic scientific constraints inhibiting life forms from evolving into sophisticated societies capable of cosmic exploration. If this conjecture bears veracity, it intimates that humanity might confront analogous insuperable obstacles, potentially precipitating our own eventual demise. The Great Filter concept proffers hypothetical impediments to the progression of sentient life. These barriers might have manifested in the past, stymieing the ascent of organisms to sapience, or they could lurk in the future, presenting an existential threat to any advanced society. This theory intimates that the smoother the evolutionary trajectory hitherto, the more formidable the forthcoming challenges confronting humanity may prove to be. At its core, if humanity has yet to confront its Great Filter, it stands to reason that such a hurdle lies ahead. Initially met with skepticism, this hypothesis challenges conventional wisdom. The smooth evolutionary trajectory witnessed on Earth implies that analogous conditions could exist elsewhere, potentially fostering the emergence of other sapient life forms. This notion finds support in the Drake equation, which estimates the presence of several dozen advanced civilizations within the Milky Way. These civilizations might have pioneered technologies akin to our own in radio astronomy or spacecraft, rendering the prospect of interstellar interaction tantalizingly feasible. Yet, despite our diligent endeavors to detect extraterrestrial intelligence, the cosmos remains reticent. This conspicuous absence of evidence finds a plausible explanation in the Great Filter, positing that this unseen obstacle may account for our failure to discern any traces of other advanced life forms in the vast cosmic expanse. The Great Filter hypothesis postulates that advanced civilizations must navigate one or more pivotal challenges throughout their evolutionary journey. The existence of such filters offers a plausible rationale for the conspicuous silence pervading our search for cosmic companions. This framework allows for the possibility that certain species may surmount the Great Filter by traversing several crucial phases. Initially, the presence of a habitable planet within its star's Goldilocks zone is imperative. Life must then emerge and evolve, leveraging complex molecules like DNA and RNA for reproduction. The transition from single-celled to complex multicellular organisms represents a pivotal juncture, as does the advent of sexual reproduction, fostering genetic diversity. These evolutionary milestones should culminate in the emergence of sophisticated organisms proficient in tool usage and technological advancement, ultimately attaining a level of sophistication conducive to space colonization. The ultimate objective is the colonization of distant planets and star systems to avert self-annihilation. Robin Hanson contends that only upon achieving space colonization can a civilization truly regard the Great Filter as a trial of the past. Presently, humanity finds itself at a crucial juncture in its evolutionary journey, confronted with the formidable imperative of extending its reach beyond Earth to ensure survival. Hansen posits that an intelligent species invariably encounters a pivotal, potentially existential barrier within one of 9 evolutionary phases. This hurdle, if insurmountable, could spell the species' demise. While humanity may have surmounted 8 of these stages, the prospect of navigating the 9th, synonymous with space colonization, remains shrouded in uncertainty and may constitute the ultimate trial that could precipitate our extinction. The Great Filter hypothesis delineates various factors that civilizations must confront to avert self-obliteration, encompassing the prevention of internal conflicts, the mitigation of irreversible environmental degradation, and the sustainable management of natural resources. This theoretical construct not only informs our conceptual understanding, but also holds practical implications for shaping our strategies in space exploration. According to this paradigm, the discovery of extinct multicellular life on celestial bodies like Mars would be disconcerting, hinting that the evolutionary stages traversed thus far might have constituted the relatively manageable obstacles, with more formidable challenges looming ahead. The simplicity of the evolutionary trajectory on other planets inversely correlates with humanity's likelihood of evolving into a spacefaring civilization. Nonetheless, the scenario isn't entirely bleak. It remains plausible that humanity has already surmounted the most formidable hurdle on its evolutionary odyssey. Consequently, some scholars contend that our apparent cosmic solitude might paradoxically signify a positive omen, suggesting that we've adeptly navigated through the treacherous shoals of the Great Filter. Nevertheless, it's imperative to acknowledge that our current modes of communication represent only a fraction of the potential methods that might exist. Across the universe's vast expanse, spanning an estimated 13.8 billion years, myriad organisms may have confronted analogous obstacles. However, their lack of awareness of one another persists, often due to the necessity of monumental technological advancements, an irony underscored by humanity's own trajectory. On Earth, our march of progress has perilously propelled us towards the precipice of potential self-obliteration, epitomized by the specter of nuclear conflict. The looming specter of our civilization's potential annihilation before the fruition of more sophisticated propulsion or communication technologies looms large. Pinpointing the elusive Great Filter proves to be a formidable task, compounded by the staggering diversity of planetary conditions across the cosmos. Abiogenesis, the intricate transition from inorganic to organic matter, emerges as a plausible candidate for the Great Filter, potentially stymieing the evolution of numerous intelligent species. In light of the Great Filter hypothesis, profound uncertainties shroud humanity's trajectory. Are we equipped to surmount an unforeseen challenge with resolute efficacy? Or have we already triumphed over the most formidable phase? Might the universe's profound silence signal that we rank among the scant species to have successfully navigated the myriad hurdles posed by the Great Filter? Alas, these inquiries persistently elude definitive answers. At present, our recourse lies solely in fortifying ourselves for the unforeseeable trials or tribulations that the cosmos may yet lay at our feet. Rare Earth hypothesis. Is complex life rare in the universe? It's truly remarkable to contemplate our existence in one of the universe's rare oases where life can thrive, where the inhospitable extremes of suffocation, freezing, burning, or dehydration don't swiftly extinguish life's flame. It's as though we've stumbled upon an extraordinary stroke of luck. Nestled comfortably within Earth's biosphere, our unique position affords us a privileged vantage point from which to behold the cosmos. This perspective offers intriguing insights into the Fermi paradox. It seems logical that we would inhabit a planet hospitable to life in a universe capable of birthing such life-sustaining worlds. The anthropic principle proposes that our presence here is no coincidence. Rather, it reflects an inherent bias toward observation. The strong anthropic principle takes this a step further, suggesting that any universe we observe must inherently possess the conditions requisite for the emergence of observers like us. We'll delve into the ramifications of this notion, which includes the contentious notion of multiple universes. However, for now, our focus rests on the weak anthropic principle, a concept of profound significance despite its seemingly modest label. It posits that our existence necessitates placement within a universe conducive to our survival, such as a planetary biosphere, rather than amidst the barren void between galaxies. Though this assertion may appear self-evident, acknowledging this observer-centric bias proves pivotal in comprehending why the universe presents itself to us as it does. When we consider the weak anthropic principle alongside the conspicuous absence of extraterrestrial civilizations, it could imply that intelligent life is extraordinarily rare in our cosmos. To grasp this, ponder the essence of being an intelligent observer. The very act of contemplating these questions constitutes a singular mental experience, an experience you're currently undergoing. The kind of consciousness you possess, your very existence, might indeed be exceedingly rare, perhaps even singular, existing only within highly specific environments. Yet here you are, experiencing this consciousness, embodying it fully. Regardless of the rarity of such life-supporting environments, you inevitably find yourself within one of them. The weak anthropic principle does not prescribe the scarcity of these environments. Consider this. If there exists only one planet teeming with life in the entire galaxy, or even across the entire universe, it's the one you would inhabit. This notion leads us to the rare Earth hypothesis, which posits that a confluence of unique factors renders Earth an exceptionally rare and ideally suited planet for nurturing intelligent life. This hypothesis finds support not just in the extraordinary characteristics of our planet, which we'll delve into shortly, but also in the conspicuous absence of extraterrestrial life. The Fermi paradox underscores the jarring contradiction between the countless potential havens for life in the galaxy and the stark dearth of evidence for other galactic civilizations. We've previously explored the Fermi paradox and its various conjectures, but let's entertain the notion that the paradox holds true as it seems. Technological civilizations are exceedingly rare, possibly because planets like Earth are exceptionally scarce. Discussions surrounding the Fermi paradox often gravitate toward the concept of the Great Filter, a series of arduous or improbable steps in the evolution from a barren planet to a technologically advanced civilization. One such filter could be an impending peril, such as climate catastrophe or nuclear holocaust, which still poses a threat to our existence. However, the rare Earth hypothesis offers a somewhat more hopeful perspective, suggesting that planets capable of nurturing civilizations akin to ours are extraordinarily rare. This idea gained prominence through the work of Peter Ward and Robert Brownlee in their 2000 book, which meticulously examines the unique attributes of Earth necessary for the emergence of life and intelligence. Before we delve into Earth's distinctive qualities, it's crucial to acknowledge what's not rare about Earth. Planets resembling Earth are actually quite common. These rocky planets, akin in size to Earth, orbit stars resembling our Sun at a distance conducive to liquid water, what scientists dub the habitable or Goldilocks zone. The Kepler mission hinted at the possibility of around 10 billion such planets in our galaxy, a number that could soar to 40 billion if we include planets orbiting other types of stars. With billions of potential nurseries for life within the Milky Way, the notion persists that if even one civilization had a slight head start over us, it could have conceivably colonized the entire galaxy by now. This notion beckons the consideration that Earth might harbor unique attributes, rendering true Earth-like planets far scarcer than we imagine. Assessing Earth's singular characteristics vital for sustaining life allows us to gauge their rarity. Should any other planet share a life-critical trait with Earth, that trait might be relatively prevalent. However, if a feature is exclusive to Earth, it could be exceedingly rare. According to the weak anthropic principle, it's hardly surprising that we find ourselves on one of the scant planets endowed with these distinctive qualities. Presently, our understanding of exoplanets remains circumscribed, so let's juxtapose Earth with the other rocky denizens of our solar system. Two conspicuous qualities distinguish Earth. One, its dynamic interior, and two, its substantial moon. At the Earth's core lies a solid iron inner core encased within a molten metal outer core. The churning within this core engenders a robust magnetic field, shielding Earth from pernicious cosmic radiation and solar tempests. Beyond the core lies the solid yet malleable mantle propelling plate tectonics, The Earth's lithosphere is partitioned into plates that drift and intermittently plunge back into the mantle, a phenomenon known as subduction. This tectonic dynamism not only precipitates alterations in ecosystems, but also fosters biodiversity by instigating environmental transitions. The recycling of nutrients from the Earth's crust into the mantle and subsequently into the atmosphere via volcanic eruptions is indispensable for upholding a fecund biosphere. In stark contrast, Mars exhibits minimal tectonic activity, while Venus, if any, is negligible, with neither planet boasting a shielding geomagnetic shield. While the frequency of tectonic activity on exoplanets remains uncertain, it's conceivable that such activity is a rarity. Earth's moon looms large in comparison to the satellites of other rocky planets in our solar system, a characteristic that might be exceedingly rare on a cosmic scale. Its dimensions, composition, and orbital path suggest it likely coalesced from the debris of a cataclysmic collision between a Mars-sized protoplanet and the nascent Earth. This cosmic crash could have wielded profound influence on the development of life on Earth, potentially shaping several pivotal facets. The impact is believed to have hastened Earth's rotation, yielding shorter nights crucial for photosynthesis and establishing Earth's axial tilt. A moderate tilt is posited to be vital for life, fostering seasons of manageable temperance. Earth's tilt appears to inhabit a Goldilocks zone, a potential rarity in the cosmos. Furthermore, the collision might have jump-started Earth's tectonic activity by fracturing its early crust. Moreover, the Moon's gravitational tugs could have intensified ongoing tectonic motions. An alternative theory proposes that the Moon played a role in abiogenesis. This hypothesis conjectures that life emerged in tidal pools, where the Moon's gravitational pull fostered conditions conducive to the genesis of intricate chemicals and protocells. Moreover, our solar system as a whole exhibits remarkable singularity. The revelations from the Kepler mission concerning other planetary systems underscore this distinctiveness. Our solar system boasts a diverse array of planet types, spanning from diminutive rocky worlds like Mercury to colossal gas giants like Jupiter and Saturn. This spectrum of celestial bodies diverges from the norm observed in other systems, where planets tend to exhibit more uniformity in size. Grandiose planets akin to Jupiter and Saturn are a rarity, constituting merely about 10% of systems. Jupiter, in particular, may have played a pivotal role in nurturing life's emergence by assuming the mantle of a cosmic guardian. Its formidable gravitational influence likely ensnared myriad comets and asteroids that might otherwise have collided with Earth, thereby averting numerous mass extinction cataclysms and potentially facilitating the unhindered march of life and evolution. Various other factors may contribute to Earth's exceptionalism, encompassing an especially conducive atmosphere, abundant water reservoirs, and the fortuitous evasion of cosmic perils such as gamma-ray bursts. However, what might truly set Earth apart within the cosmic tapestry is the singular trajectory of its evolutionary saga. Life, particularly in its nascent forms, could be widespread, but the transition from rudimentary organisms to complex life forms or the blossoming of intelligence might entail exceedingly rare evolutionary leaps. A notable instance of such rarity is the genesis of the eukaryotic cell, believed to have been a unique evolutionary event wherein two simpler cell variants merged, with one cell evolving into the mitochondria. This fusion precipitated a quantum leap in cellular complexity, ultimately paving the way for the emergence of multicellular organisms. Throughout Earth's evolutionary journey, several pivotal moments have shaped the trajectory of life on our planet. Events like the Cambrian explosion, the asteroid impact that wiped out the dinosaurs, and other potential turning points have significantly influenced the development of life as we know it. Earth appears to have navigated these junctures with a stroke of luck, leading to its unique evolutionary path. The rare Earth hypothesis delves into the role luck may have played in Earth's development. Many of the characteristics that make Earth conducive to life and the milestones in its evolutionary history appear to be one-of-a-kind occurrences. According to the weak anthropic principle, these events could be exceptionally rare. Until we gather more evidence, ideally by observing similar events elsewhere or witnessing them occur again, we cannot assume their likelihood. The combination of these improbable factors raises the possibility that intelligent life in the universe is exceedingly rare. This perspective offers a potential solution to the Fermi paradox, suggesting that the apparent emptiness of the galaxy might be a true reflection of reality. It's plausible that we find ourselves on the only habitable planet in the cosmos, gazing out from our extraordinary Earth into the vast, seemingly uninhabited expanse of the universe. Is planet Earth a zoo for aliens? Cosmic quarantine hypothesis. The Fermi paradox raises a perplexing question. If extraterrestrial life is likely, why haven't we made contact with advanced civilizations? One intriguing theory, the zoo hypothesis, proposes that alien life exists but intentionally remains hidden, treating Earth as a sanctuary. But why would they stay hidden? One reason could be a fear of interplanetary contamination, similar to our concerns about microbes from Earth disrupting other planets. Ecosystems. To maintain ecological balance, aliens might observe us from afar, avoiding direct contact. Communication challenges also factor in. The vast differences between species could lead to confusion or fruitless interactions. Therefore, aliens might prefer covert observation to prevent misunderstandings or disruptions to our natural development. Some interpretations suggest that aliens known as watchers passively observe Earth for scientific study or to allow our civilization to evolve without interference. Alternatively, they might monitor without engaging, deeming us too primitive for direct contact. Another explanation posits differences in timescales. Aliens could be visiting Earth infrequently, perhaps every few thousand or million years, leaving no lasting evidence. The slow reveal theory within the zoo hypothesis suggests that a sudden introduction to advanced alien civilization could be disastrous for humanity. Thus, aliens might opt for a gradual approach, allowing us time to adapt to their existence. The lack of contact with extraterrestrial life could be due to ancient taboos among alien cultures, prohibiting contact with less advanced civilizations. This tradition might have originated from a dominant ancient civilization in the galaxy, setting a precedent for younger civilizations. Advanced aliens might only intervene in our development when absolutely necessary to minimize risks in first contact and avoid technological dangers we haven't fully grasped. The preservation hypothesis suggests that civilizations maintain isolation to preserve cultural and technological diversity. Too much interaction could lead to a loss of uniqueness. Cultural factors, like xenophobia or religious beliefs, might also influence the zoo hypothesis dynamics, leading to periods of isolation or unpredictable behaviors in response to cosmic events. Another theory is that intelligent life beyond Earth is extremely rare or non-existent, either naturally or due to a dominant civilization suppressing others. Alternatively, the universe might be a simulation, with Earth as the focal point. Lastly, the laboratory hypothesis proposes that our universe is a controlled environment designed by unknown forces, possibly as part of an elaborate experiment. These perspectives on the zoo hypothesis offer different explanations for the Fermi paradox, providing unique insights into why we haven't encountered extraterrestrial life. Are aliens deliberately avoiding contact with us? Dark forest hypothesis. The universe is vast, with numerous planets that could potentially support life. Despite this, we haven't detected any signs of extraterrestrial life, leading to what's known as the Fermi paradox. This paradox arises from the fact that if even one advanced alien civilization could travel at a fraction of the speed of light, it could have spread throughout our galaxy in a relatively short time compared to its age. Yet, we see no evidence of such civilizations. One possible explanation for the Fermi paradox is the dark forest theory. This idea suggests that while the universe may indeed be teeming with life, civilizations may choose to remain hidden from each other. This caution stems from the competitive nature of life itself. On Earth, organisms compete for survival, resources, and the chance to reproduce. This competition has led to the dominance of certain species, like humans, who have a knack for innovation and resourcefulness. However, this dominance also comes with unintended consequences, such as the extinction of numerous species due to human activities. In a universe where every civilization strives to survive and expand, Revealing oneself could be perilous, akin to a lone hunter in a dense, foggy forest, hesitant to call out for fear of attracting unseen predators. Humans, like other beings, form cultures that engage in their own brand of competition. Cultures driven by competition and expansion tend to spread rapidly, often absorbing, dominating, or wiping out others. Our history illustrates this. Humanity poses a threat not just to other species, but to itself. Motivated by our instincts, we've colonized every corner of Earth and are now setting our sights on the cosmos, seeking new territories and resources. It's likely that this competitive spirit isn't unique to Earth, suggesting that an alien civilization that has conquered its own planet may share similar traits with humans, including potential danger. Just as a lone hunter moves cautiously through a dark, dense forest, aware that others like him might be lurking, unable to discern their intentions but assuming they might act aggressively for survival, so too must we approach the possibility of encountering other civilizations in space. This scenario implies that in a chance encounter, taking preemptive action might be a survival strategy. However, this doesn't mean conflict is inevitable. Human progress suggests that we become more peaceful over time. This trend could hold true for other civilizations, where advancement leads to decreased conflict. Alien civilizations could vary from benevolent and peaceful to hostile and militaristic. The crux of the matter in interstellar encounters is the uncertainty of intentions. We cannot easily determine whether an alien civilization is peaceful or aggressive, just as they might misunderstand or distrust our peaceful gestures. This ambiguity presents a significant existential challenge when encountering others among the stars. Moreover, the challenge of communicating with and encountering alien civilizations is compounded by the vast distances of light years, resulting in significant delays. These delays raise uncertainty, prompting consideration of preemptive attack as a potentially safer strategy. This concern is amplified by the unpredictable pace of technological advancements and the concept of gaining an advantage through striking first. Throughout history, technological progress has been pivotal in warfare, often leading to one-sided annihilation. From ancient legions to modern drones and guided missiles, advancements continually outpace previous military technologies. In the context of interstellar conflict, the time it takes to deploy an invasion fleet across light years means that by the time it arrives, it could be outdated. Consequently, wars between civilizations may focus on eliminating the other as an existential threat. The fear of a preemptive strike from the other side could prompt a rapid and overwhelming assault to prevent retaliation or future reprisals. The gravity of such situations allows no room for error. Assuming most civilizations are planet-based, they become susceptible to devastating weapons capable of annihilating entire planets. One such example is the relativistic kill vehicle, a missile traveling at a substantial fraction of the speed of light. A missile of human scale, traveling at 95% the speed of light, would possess energy equivalent to Earth's entire nuclear arsenal. Just a few of these missiles could ensure the destruction of a targeted civilization, with even a single strike potentially being catastrophic. Such weaponry is not beyond the capabilities of civilizations only slightly more advanced than our own. These weapons are particularly menacing because they heavily favor a first strike approach, making defense or countermeasures nearly impossible once launched. Interstellar conflicts could thus be swift and decisive, with the initial aggressor often emerging victorious. This reality underscores the potential existential threat posed by every civilization to others. In a universe like ours, civilizations might fall into two categories: those that remain silent and those that have perished. So, what should our approach be? Currently, it's unlikely that extraterrestrial civilizations have detected humanity. Our radio signals, spanning just a century, have traveled only a negligible distance in the cosmic expanse and have likely dissipated into background noise. At our present technological level, staying unnoticed is probable if we avoid drawing attention and if no one specifically targets our unremarkable solar system. However, as we venture further into space exploration, these questions demand reconsideration. We're uncertain whether we're alone in this vast forest or not. For now, the most prudent path forward is cautious observation. If we detect another civilization revealing itself, our response should be measured and careful, observing from a distance before engaging further. However, it's conceivable that our perspective is clouded by our primitive competitive instincts, which may be painting an excessively fearful picture of potentially predatory alien civilizations. It's plausible that, as a species, we're not yet mature enough to grasp the true nature of the universe. There might await a friendly galaxy for us once we attain that readiness. At present, the imperative is clear. Exercise caution in the signals we transmit into space, keep a vigilant eye on the skies, and deepen our understanding of the galactic forest. Whether this forest is fraught with peril, filled with potential allies, or entirely devoid of other life forms, only thorough observation and study will unveil the truth. Let's hone in on this scenario. In the clearing, the hunter confronts another being, both gripped by fear. In this intense moment, the hunter pauses, taking a deep breath, and makes a choice. Perhaps the path out of the dark forest lies in stepping into the clearing together, opting for collaboration rather than confrontation. Can the James Webb Space Telescope find signs of alien life? The James Webb Space Telescope, in less than a year since its launch, has already exceeded expectations with its remarkable images of distant galaxies, nebulae, exoplanet atmospheres, and deep space fields. Its capabilities are unmatched in detail and sensitivity. Now it's embarking on an exciting new task, searching for signs of life beyond Earth. Using its advanced infrared technology, the Webb telescope will closely examine distant planets for chemical signals that could indicate the presence of life, known as biosignatures. This phase of the mission represents a significant step forward in our exploration of the cosmos and our position within it. The Webb telescope has four main methods for potentially detecting extraterrestrial life: identifying essential chemicals for life, detecting substances produced by biological processes, looking for elements necessary for a stable climate, and finding unusual chemical combinations that don't typically occur together. Scientists have primarily focused on studying planets similar to Earth, located within their star's habitable zones, where conditions might support liquid water. With cutting-edge telescopes like Webb, equipped with precise optics and infrared imaging, the focus of exoplanet exploration is shifting from mere discovery to a deeper analysis of their characteristics. This advanced examination involves directly capturing images of exoplanets and studying their atmospheres using spectroscopic data. Since the 1800s, scientists have known that specific chemicals absorb and emit light at distinct wavelengths. By analyzing the chemical composition of exoplanet atmospheres, researchers can gain more insight into their potential habitability. The Webb telescope is gearing up to search for four key chemical indicators in its quest for signs of life: oxygen and ozone, phosphine and ammonia, methane and carbon dioxide, and chemical imbalances. Oxygen is particularly important as a biosignature because of its crucial role in life processes. Earth's history provides a fascinating example. Initially, our atmosphere was rich in carbon dioxide, creating what's known as a reducing atmosphere that hindered oxidization. However, the emergence of cyanobacteria and other photosynthetic organisms gradually transformed this, leading to the Great Oxygenation Event around 2.4 to 2.0 billion years ago. This shift from a reducing to an oxidizing atmosphere played a pivotal role in the evolution of life on Earth, enabling the development of more complex organisms over time. Additionally, the interaction between oxygen and ultraviolet radiation in our upper atmosphere led to the formation of the ozone layer, which now protects life on Earth from harmful UV radiation. However, it's important to note that detecting these molecules in the atmosphere of an exoplanet doesn't guarantee the presence of life. Studies have shown that there are non-biological processes, abiotic processes, that can lead to the creation of oxygen and other molecules in a planet's atmosphere. For example, the runaway greenhouse effect can occur when surface water evaporates, leading to increased heating and further evaporation, creating a feedback loop that can result in significant water vapor in the atmosphere. When exposed to solar radiation, this water vapor can undergo photolysis, breaking down into hydrogen and oxygen gases. In one scenario, hydrogen may escape into space, leaving behind oxygen. Another possibility arises for planets tidally locked within their star's habitable zone. Intense radiation on the star-facing side can lead to photolysis, resulting in an atmosphere rich in abiotic oxygen. Surprisingly, oxygen, essential for many life forms, was toxic to the early photosynthetic organisms on Earth, suggesting that high oxygen levels could impede the development of life. Ammonia and phosphine, naturally occurring in gas giants' atmospheres and their icy moons, are also produced by life on Earth. Phosphine has gained attention as a potential biosignature after its detection in Venus's atmosphere. However, these gases exist in small amounts on Earth, posing a challenge for detecting them in the atmospheres of distant exoplanets. Methane and carbon dioxide are also considered potential signs of life, especially when found together, as they originate biologically on Earth. Methane arises from organic decomposition and digestion processes, while carbon dioxide is a product of respiration in oxygen-consuming organisms. Furthermore, carbon dioxide plays a crucial role in regulating temperatures on a planet. Imbalances in its concentration can lead to extreme climate conditions like a runaway greenhouse effect or glaciation. Finally, chemical imbalances in an exoplanet's atmosphere could indicate the presence of life. Life disrupts chemical equilibrium by consuming certain substances and producing energy and byproducts. This idea aligns with the Gaia hypothesis proposed by planetary scientist James Lovelock, who suggested that true chemical stability is typically found in lifeless systems or planets, using Mars as an example to illustrate this concept. Another potential biosignature not highlighted by Barstow is hydrogen. Recent studies from Cornell University suggest that volcanic hydrogen in an exoplanet's atmosphere might expand the habitable zones around stars. Hydrogen gas acts as a natural greenhouse gas, and volcanic activity is seen as crucial for life's emergence. Additionally, research from the University of Cambridge has introduced the concept of Hycean planets, ocean worlds with hydrogen-dominated atmospheres, as promising candidates in the hunt for extraterrestrial life. However, the presence of these chemicals in an exoplanet's atmosphere should not automatically be seen as proof of life. Barstow stresses the complexity and precision required in exoplanet research. Accurately measuring the quantities of these gases is challenging because their signals can overlap and demand careful separation for analysis. She underscores that the James Webb Space Telescope is just beginning to unveil a vast new realm of planetary atmospheres. Through this exploration, many existing assumptions about exoplanets and their atmospheres are likely to be reassessed or even debunked. Is finding alien life closer than we think? The quest to uncover extraterrestrial life has evolved from questioning its existence to contemplating when it might be discovered, marking a significant shift in the focus of modern astronomy. There's a growing optimism among scientists that signs of life on distant worlds could potentially be detected within our lifetimes, with some suggesting it could happen in the next few years. This increased anticipation is fueled by recent advancements and missions in space exploration. For example, the James Webb Space Telescope has provided promising indications of potential life on an exoplanet. This telescope, along with other missions, heralds a new era in space exploration, one centered around what could be one of the greatest scientific discoveries. Considering the vastness of the universe, with its countless stars and planets, it's logical to assume that Earth might not be the sole harbor of intelligent life. Today's advanced technology and exploration capabilities have brought humanity to a crucial juncture where answering the profound question of our cosmic solitude is more feasible than ever. This current phase in space exploration transcends mere exploration. It's also about the pursuit of discovering life beyond our planet in the vast expanse of the universe. Telescopes now have the capability to analyze the atmospheres of distant exoplanets, searching for chemicals typically associated with living organisms on Earth. A recent example is the detection of a gas on the exoplanet K218b, situated 120 light-years away, which bears similarity to one produced by marine organisms on Earth. K218b resides in the Goldilocks zone of its star, where conditions are just right for liquid water to exist, a critical factor for supporting life. Scientists anticipate confirming the validity of these initial signs of life within a year. The lead researcher from the Institute of Astronomy at Cambridge University suggests that such confirmation would profoundly alter the approach to seeking extraterrestrial life, hinting that life might be more widespread in the universe than previously believed. Even if K218b doesn't yield signs of life, there are 10 more planets in the Goldilocks zone awaiting examination, and each outcome, positive or negative, will provide valuable insights into the potential for life on these worlds. This project is just one of many endeavors aimed at detecting signs of life in the universe, with some concentrating on our solar system and others venturing into deep space. While telescopes like NASA's James Webb Space Telescope boast impressive capabilities, they have limitations, especially in detecting smaller Earth-like planets near their stars due to glare. NASA intends to launch the Habitable Worlds Observatory in the 2030 equipped with technology to minimize starlight and analyze Earth-like planet atmospheres. Another significant advancement is the European Southern Observatory's extremely large telescope, to be stationed in the Chilean desert. Its vast mirror will facilitate detailed observations of planetary atmospheres. These advanced telescopes employ a centuries-old technique used by chemists to identify chemicals based on the light they emit, enabling the analysis of light from hundreds of light years away. In addition to examining distant exoplanets, some missions concentrate on the icy moons of Jupiter and Saturn, deemed promising for extraterrestrial life. NASA's Clipper and the European Space Agency's Jupiter Icy Moons Explorer missions are scheduled to explore Europa, one of Jupiter's moons, in the early 2030 ES. Europa, with its subsurface ocean and water vapor plumes, stands as a prime contender in the quest for life beyond Earth. NASA is gearing up to send the Dragonfly spacecraft to Titan, one of Saturn's moons, renowned for its abundance of carbon-rich chemicals and potential for sustaining life. Meanwhile, though currently harsh, Mars is believed to have once harbored conditions conducive to life. NASA's Perseverance rover is collecting samples from a crater that may have once been an ancient river delta, with plans to return these samples to Earth for analysis in the 2030 Beyond our solar system, the quest for radio signals from alien worlds persists, spearheaded by institutions like the Search for Extraterrestrial Intelligence, SETI Institute. The James Webb Space Telescope's prowess in pinpointing promising locations for alien civilizations has reinvigorated SETI's search endeavors, now employing cutting-edge technology to detect potential communications from distant planets. While some scientists maintain skepticism regarding the likelihood of receiving a clear signal from extraterrestrial life, the prospect remains a captivating and unequivocal means of confirming life beyond Earth. The last 3 decades have witnessed a revolution in our comprehension of exoplanets, and the detection of life signs would represent a monumental scientific leap, reshaping humanity's understanding of its cosmic significance. Mysterious expanse brimming with phenomena that constantly defy our understanding. From the intricacies of quantum mechanics to the enigmatic properties of black holes, the universe presents a plethora of perplexing puzzles that stretch the limits of our comprehension. This video acts as a portal into the intricacies of the cosmos, shedding light on the mysteries and surreal contradictions that endure despite our earnest attempts to decipher them. In the early stages of the universe, things looked quite different. Gas and dark matter clouds were just starting to come together under the influence of gravity. This was also the time when the first stars, made up primarily of hydrogen and helium, began to form. Surprisingly, even at this early stage, some incredibly massive black holes, weighing up to 1 billion times the mass of our Sun, had already emerged. According to our current understanding of how black holes form and grow, it should take billions of years for a black hole to reach such immense proportions. However, since the universe is less than 1 billion years old, this poses a puzzle. According to existing models, quasars and other supermassive black holes shouldn't have existed during this early period. But observations tell us otherwise. So how did these colossal black holes come into being? How did they gain so much mass in such a short time? And what does this newfound information mean for our understanding of black hole formation? Before delving into those questions, let's clarify what a quasar is. A quasar is essentially a supermassive black hole that spins rapidly and consumes surrounding matter, emitting intense radiation in the process. They are incredibly bright and powerful cosmic phenomena, often billions of times brighter than our own Milky Way galaxy. The key to understanding their strength lies in their environment. Quasars are typically found in galaxies with abundant gas reservoirs. As this gas falls into the black hole, it heats up and emits radiation across various frequencies. This process occurs predominantly in distant galaxies because local supermassive black holes usually lack the necessary gas supply. For example, Markarian 231, one of the closest quasars, is still about 600 million light-years away. The question at hand is, how do black holes, these magnificent cosmic phenomena, come into existence? Currently, there are two primary theories explaining their formation. The first theory, widely accepted, suggests that when a massive star dies, it can collapse under its own gravity, forming a black hole. Initially, these black holes might have a mass up to about 100 times that of our Sun. Over time, they can grow larger as they consume nearby matter, eventually reaching a supermassive state with a mass millions to billions of times greater than the Sun. However, experts have determined that even with ample time, a black hole couldn't accumulate matter fast enough to grow to the size of a billion suns in just 500 million years. This is due to the formation of an accretion disk, a swirling ring of matter that forms around the black hole as it consumes material. The intense gravitational forces within this disk cause it to heat up and emit various types of radiation. This radiation exerts a powerful outward force which counteracts the inward pull of gravity, slowing down the rate at which the black hole can consume matter. This upper limit on a black hole's growth rate is known as the Eddington mass. Even if a black hole manages to consume matter at a rate exceeding this limit, the excess accumulation would likely result in powerful outflows of energy, blowing away nearby material and halting further growth. Thus, the growth rate of black holes is constrained by these factors. If this scenario occurs, it challenges the conventional understanding of how quasars, intensely bright objects powered by supermassive black holes, formed in the early universe. Now let's delve into an alternative theory explaining the origins of quasars. This hypothesis suggests that black holes ranging in mass up to 100,000 times that of the Sun could have formed from the collapse of short-lived stars. Some of these stars, possibly with lifespans nearing 250,000 years, might have collapsed into massive black holes. Given their enormous size, these black holes could have rapidly accumulated billions of times the mass of our Sun. Support for this idea comes from estimates indicating that quasars must have had initial masses between 10,000 and 100,000 times that of regular stars, which aligns with this hypothesis. However, for such colossal black holes to form, the parent stars would need to be incredibly massive, tens of thousands of times larger than the Sun. Yet, no such massive stars have been observed in our observable universe. Even the largest star on record is only about 300 times the size of our Sun. Nevertheless, conditions in the early universe differed significantly from what we observe today. Simulations suggest that under these early conditions, massive stars could have emerged at the convergence points of dense, turbulent streams of cold gas. While this scenario would have been rare, it provides a potential explanation. However, for stars to form under these circumstances, highly unusual conditions such as intense ultraviolet radiation or extremely fast movements between gas and dark matter would have been necessary. Moreover, none of the environments known to us today resemble those where the first quasars were discovered. So despite these challenges, how do we explain the appearance of quasars in the early universe? Scientists conducted simulations to address this question. Typically, a new star forms when a dense mass within a cool gas cloud collapses due to gravity. However, if there is significant turbulence present, this collapse can be disrupted. The simulation revealed that the turbulence caused by the intersection of streams prevented the formation of typical stars we see today. Instead, the cloud expanded to such an extent that it violently fragmented into two massive stars, approximately 31,000 and 40,000 times the mass of the Sun. In this scenario, if the gas from the streams continues to fuel the clouds, A supermassive black hole, billions of times the mass of the Sun, can develop and grow rapidly within a few 100 million years. This sheds light on how supermassive black holes could have formed at the intersections of gas streams, even without extraordinary circumstances. According to estimates, around 200 quasars could have emerged within the first billion years of the universe's existence. One of the study's authors, Daniel Whalen, summed it up by stating, "The first supermassive black holes were merely a natural result of structure formation in cold, dark matter cosmologies, offspring of the cosmic web." This concept is remarkable. If you're still watching, be sure to subscribe and like the video. Thank you so much. Let's continue. A supernova is like the grand finale of a star's life, marking its most spectacular and powerful moment. Picture this: a massive star, at least 5 times the size of our Sun, reaches the end of its life cycle and explodes in a colossal burst of energy and light. Now, what leads to this dramatic explosion? Well, massive stars are like cosmic powerhouses burning through vast amounts of nuclear fuel at their cores. This process generates immense heat and pressure, which keeps the star from collapsing under its own gravity. It's a delicate balance between gravity trying to crush the star inward and the energy from nuclear reactions pushing outward. But eventually the star exhausts its nuclear fuel. With nothing left to sustain it, the balance is disrupted and gravity takes over. The star collapses in on itself with staggering speed, like a building crumbling in a fraction of a second. This collapse sends shock waves rippling outward, triggering the star's outer layers to erupt in a dazzling display of light and heat. What's left behind after this cosmic fireworks show is a dense core and a rapidly expanding cloud of hot gas known as a nebula. This remnant serves as a testament to the colossal forces at play in the universe, marking the end of one star's journey and the birth of something new amidst the chaos of creation. A supernova can result in the formation of incredibly dense objects called black holes, which are among the densest entities in the universe. Imagine yourself as an astronomer in the early 17th century, a time before the invention of telescopes. With limited tools, you're peering into the night sky, trying to uncover the mysteries of the cosmos. Then, one remarkable day, you witness an extraordinary sight. A new star appears, shining brighter than Venus and even visible during daylight. Over the following weeks, it remains prominent in the sky, gradually dimming but still perceptible. This phenomenon was observed by astronomers across Europe, the Middle East, and Asia, including the renowned Johannes Kepler in 1604. Today, we understand that what they witnessed was not the birth of a new star, but rather a supernova explosion, a colossal event marking the end of a star's life cycle. The most recent supernova observed within our own galaxy occurred in 1604. While it's possible that other supernovae have since occurred nearby, they may have gone unnoticed due to obscuration by interstellar gas and dust. The Crab Nebula serves as a poignant example, as it is the remnant of a supernova that exploded around the year 1054, its light reaching Earth centuries later. In 1987, astronomers observed a supernova in the Large Magellanic Cloud, providing a rare glimpse into a phenomenon akin to Kepler's supernova. Furthermore, astronomers have documented several supernovae in distant galaxies, although these can only be observed with the aid of telescopes. Such events would have eluded the observation of skywatchers in Kepler's era, highlighting the remarkable advancements in astronomical technology over the centuries. It's been a staggering 418 years since the last time we observed a star exploding in our galaxy. Considering that typically we expect between 1 to 3 such explosions every century, we're long overdue for a spectacular supernova event. Luckily, modern astronomers are in a far better position to study such an event than their predecessors like Kepler or scientists from just a few decades ago. Today's astronomers have access to advanced telescopes that can capture visible light, enabling them to simulate the experience of being near a supernova and observing it firsthand. Moreover, they also have tools sensitive to infrared light, which has longer wavelengths and can penetrate gas and dust more effectively than visible light. This capability allows astronomers to see objects that might be obscured from view with conventional telescopes. For instance, the James Webb Space Telescope primarily records in the infrared spectrum. Beyond light observation, modern detectors can capture other emissions from supernovas, such as neutrinos, which are subatomic particles, and gravitational waves, tiny vibrations in space-time. In the scientific realm, two main types of supernovas have been identified. Type 1 supernovas occur when a white dwarf star pulls material from a companion star until a runaway nuclear reaction blows the white dwarf apart. On the other hand, Type 2 supernovas happen when a star collapses under its gravity as it runs out of nuclear fuel, triggering a powerful explosion. In some cases, supernovae can outshine their entire host galaxies. Type 2 supernovae are particularly intriguing because they emit an immense amount of neutrinos along with light. Interestingly, neutrino emissions can start even before the explosion itself. Back in 1987, when neutrino research was still in its early stages, 3 detectors managed to capture about 24 neutrinos from a supernova explosion. If a similar event were to occur today within our galaxy, we could potentially detect hundreds or even thousands of neutrinos using the global network of detectors, offering significant insights. However, if a collapsing star forms a black hole instead of exploding, the emission of neutrinos abruptly stops. Detecting this sudden cessation of neutrinos could indicate the formation of a black hole. By comparing the missing star to entries in astronomical databases, we might identify it as the location of a newly formed black hole. Furthermore, if we were to successfully detect gravitational waves from such a galactic explosion, it would mark a significant achievement. Gravitational waves predicted by Einstein are ripples in spacetime caused by the acceleration of massive objects. They were first detected in 2015, primarily originating from mergers between black holes and neutron stars. This trifecta of discoveries, neutrinos, black holes, and gravitational waves, provides valuable insights into the universe's most dramatic events. When a supernova happens in our galaxy, it's a significant event that astronomers expect to observe. Despite astronomers using computer models to understand supernova explosions for years, many aspects of these events remain mysteries. However, studying gravitational wave data could provide valuable insights into this phenomenon. Concerning the potential threat to Earth from a nearby supernova, theoretically, it could pose a danger. However, the likelihood of this is currently low because there are no stars close enough to Earth that are at risk of exploding. Nonetheless, if a supernova did occur nearby, its radiation could be catastrophic. The release of harmful UV, X, and gamma radiation over several weeks could damage Earth's ozone layer. Even if these radiations didn't reach the surface, the depletion of the ozone layer would expose life on Earth to lethal levels of UV radiation from the sun, endangering everything from oceanic phytoplankton to humans. There's evidence suggesting that a supernova may have caused a mass extinction event around 360 million years ago, near the end of the Devonian period. However, supernovae aren't solely destructive. They also play a crucial role in the creation of new elements essential for life. Astronomers and physicists highlight that the nuclear processes occurring within exploding stars and the subsequent dispersal of heavy elements throughout space contribute to the formation of elements vital for human existence. In the broader narrative of the universe, supernovae serve as pivotal events. Approximately 13.7 billion years ago, the Big Bang set the universe in motion, initiating the formation of atoms, stars, and galaxies, marking the beginning of the cosmic tale. What unfolds here is a uniquely human saga, stretching across millennia as we strive to comprehend the universe. Guided by the principles of science, this endeavor has allowed us to grasp our position within the vast cosmos. Over thousands of years, we've meticulously recorded our observations of the heavens, amassing a library's worth of knowledge about the universe's origins and eventual fate. So where does our story begin? Let's embark on this journey from the very beginning, diving into the genesis, starting with the monumental event known as the Big Bang. The concept of the Big Bang serves as a framework for understanding the cosmic evolution, revealing how the universe transformed in an instant. Yet the exact cause of this cosmic genesis remains a puzzle to this day. As we gaze into the depths of the universe and ponder distant galaxies, we witness a captivating panorama of celestial motion. Everything seems to be moving away from us, expanding at incredible speeds. Tracing this expansion back, we glimpse a moment some 13 or 14 billion years ago when all matter was densely packed into an unimaginably small point. The Big Bang stands as our leading theory, a testament to our efforts to unlock the secrets of the universe's birth. For a long time, contemplating the universe's origin wasn't a widespread pursuit. Some paid it little mind, while others believed the cosmos had always existed, an eternal enigma. Initially, even scientists were cautious about embracing the concept of the Big Bang. Originally coined somewhat mockingly, the term itself presents a paradox. It wasn't exactly big, considering the belief that the universe began from a singularity and there was no literal bang, since there was no medium-like air to transmit sound vibrations. However, today, the Big Bang theory stands as a cornerstone of scientific understanding, widely accepted and comprehended. Yet, while the theory has solidified its place in our knowledge, it hasn't unveiled all the mysteries surrounding the birth of our cosmos. Traditional Big Bang theory doesn't address what initiated the event, why it happened, or what came before it. In the present moment, we inhabit the aftermath of the Big Bang. Everything we experience, sights, sounds, tastes, smells, and touches, is part of this aftermath. Here we are on Earth, a remarkable planet made up of silicon and oxygen, enveloping a metallic core. Its surface is adorned with vast oceans teeming with diverse life forms. In a graceful ballet, Earth completes a full rotation every 24 hours while orbiting the luminous star we call the Sun, completing a journey around it every 365 days. The Sun, a radiant behemoth primarily composed of hydrogen and helium, boasts a searing surface temperature approaching 10,000 degrees Fahrenheit. This cosmic furnace converts an astounding 700 million tons of hydrogen into 695 million tons of helium every single second. This radiant star lies at the core of our solar system, which formed around 4.5 billion years ago. Our solar system comprises 8 diverse planets, ranging from the scorching Mercury to the icy Neptune. But it's not a static entity. It hurtles through space at a remarkable 134 miles per second, nestled within the vast congregation of stars and systems known as the Milky Way galaxy. Within this galaxy, containing around 200 billion stars, an estimated 6 billion might possess planetary systems akin to ours. Our solar system, located on one of the Milky Way's outer arms, is just a small part of this grand cosmic ensemble. Yet the Milky Way is just a single entity among the immense expanse of over 125 billion galaxies in the observable universe. Indeed, the universe is vast, continually expanding. If we rewind time, we witness this expansion in reverse from cosmic to galactic scales, then to our solar system's dimensions, and further down to the scale of a studio, a coffee cup, and ultimately an atom. The universe's vastness unfolds before us, a cosmic narrative spanning unimaginable scales. Physicists have crafted an approximate timeline of significant cosmic events using telescope data and particle physics models, from the universe's birth to its eventual demise. One pivotal moment was the cosmic inflation era, where the universe rapidly expanded. This period of inflation, though mostly theoretical, has gained traction among cosmologists as a possible explanation for the universe's uniformity across vast distances. Efforts to detect this expansion in early cosmic light were reported in 2014, although further investigation revealed that interplanetary dust was responsible for the observed phenomena. In the early stages of the cosmos, the temperature soared to a staggering 7 trillion to 10 trillion degrees Fahrenheit, or 4 trillion to 6 trillion degrees Celsius, just milliseconds after the Big Bang. At these extreme temperatures, quarks, fundamental particles typically confined within protons and neutrons, were liberated, roaming freely. These quarks joined forces with gluons, carriers of the strong force, in a primordial concoction that filled the entire universe. Scientists have recreated these conditions in terrestrial particle accelerators, mimicking the early cosmos. However, this fleeting state lasted only for a fraction of a second. Following the initial burst, the universe entered a period of intense activity, beginning roughly a few thousandths of a second after the Big Bang. As the universe expanded and cooled, it became conducive to the formation of protons and neutrons from quarks. Approximately 1 second after the Big Bang, the cosmic neutrino background emerged, a phenomenon yet to be directly detected, allowing neutrinos to traverse space without interaction. Within the first 3 minutes of the universe's existence, the fusion of protons and neutrons produced the isotope of hydrogen known as deuterium, along with helium and trace amounts of lithium. As temperatures cooled down, around 380,000 years post-Big Bang, hydrogen and helium atoms could finally bind with free electrons, forming the first neutral atoms. This significant transition marked the birth of the cosmic microwave background, first recognized in 1965. During this epoch, photons previously scattered by electrons could travel freely, creating the cosmic microwave background. Subsequently, the cosmos entered a phase known as the Dark Ages, a period of about 100 million years where virtually no light was emitted. Studying this era poses a formidable challenge, as astronomers rely heavily on starlight to unravel cosmic mysteries. The emergence of the first stars marked a pivotal moment around 180 million years after the Big Bang. As hydrogen and helium compressed into massive spheres, extreme temperatures formed at their cores. The intense radiation from these early stars and galaxies broke apart neutral hydrogen atoms, initiating a period known as cosmic dawn or reionization. Pinpointing the exact time frame of reionization is difficult due to its proximity to the Big Bang, with its signals obscured by subsequent cosmic phenomena. However, scientists estimate that reionization concluded roughly 500 million years post-Big Bang. Nearly a billion years after the Big Bang, supermassive black holes formed at the hearts of merging galaxies. Intensely luminous quasars, visible from distances of 12 billion light-years, illuminated the cosmos. Over the subsequent billions of years, the universe continued to evolve. Gravity drew material into denser regions, leading to the formation of galaxy clusters and vast filaments of gas and dust, creating the intricate cosmic web that we observe today. The birth of our solar system traces back approximately 4.5 billion years ago, when a swirling cloud of gas coalesced into a yellow star with encircling rings in a single galaxy. Over time, these rings merged to form the 8 planets of our solar system, along with numerous comets, asteroids, dwarf planets, and moons. The third planet from the Sun, Earth, either retained a significant amount of water during this process or received it later through collisions with icy comets. This watery world became the cradle for life, with primitive bacteria emerging between 3.8 and 3.5 billion years ago. From these humble beginnings, life on Earth evolved and flourished. Primitive organisms evolved into complex marine creatures and towering dinosaurs that roamed the land. Eventually, around 200,000 years ago, Homo sapiens emerged, upright beings capable of contemplating the mysteries of the universe and unraveling its origins. However, this isn't the end of the story. The future of the cosmos remains shrouded in uncertainty for physicists. Much depends on our ability to understand dark energy, the enigmatic force believed to be driving the universe's accelerated expansion. As we continue to explore and learn, the narrative of the cosmos continues to unfold, offering endless avenues for discovery and understanding. The fate of the universe holds various intriguing possibilities. If the universe continues to expand indefinitely, eventually all stars will burn out, and even black holes will fade away into nothingness. This would leave behind a desolate cosmos devoid of life, saturated with dormant energy. Alternatively, there's the concept of the Great Crunch, a scenario where gravity triumphs over the expansive force of dark energy, leading to a reversal of the Big Bang. Another possibility is the Great Rip, where the cosmos tears itself apart as dark energy accelerates everything to ever greater distances. The universe, vast and enigmatic, harbors countless wonders and secrets awaiting discovery. Among these mysteries, one of the most profound is the age of the universe itself. Scientists have dedicated decades to studying the cosmos, employing various tools and techniques to unlock its secrets. Through their efforts, they've estimated the universe's age to be approximately 13.8 billion years. The quest to determine the universe's age began in the early 20th century when astronomers recognized its expansion. Belgian astronomer Georges Lemaitre first proposed the idea of an expanding universe in 1927, but it was the work of American astronomer Edwin Hubble in the 1920s and 1930s that solidified this concept. Hubble's groundbreaking observations of distant galaxies revealed their recession velocities, establishing Hubble's law and confirming the universe's dynamic nature. The concept of an expanding universe naturally led scientists to ponder its age. Initially, attempts to estimate its age relied on models of stellar evolution. Scientists reasoned that by studying the properties of stars in our galaxy, they could gauge the universe's age, given the predictable sequence of changes stars undergo as they age. However, these early estimates were fraught with uncertainties due to gaps in our understanding of stellar evolution, resulting in wide-ranging estimates from a few million to several billion years. It wasn't until the 1960s that a more precise method emerged. In 1964, astronomers Arno Penzias and Robert Wilson stumbled upon a faint background radiation permeating all directions of the sky. This radiation, dubbed the cosmic microwave background, CMB, is believed to be residual radiation from the Big Bang, the universe's birth event. The discovery of the CMB was a watershed moment, offering scientists a potent tool for gauging the universe's age. By scrutinizing the properties of the CMB, scientists could glean vital insights into the early universe, including its temperature and composition. This data, in turn, enabled them to make more accurate estimates of the universe's age. In the ensuing decades, scientists honed their measurements of the cosmic microwave background, CMB, and deepened their grasp of the early universe. They also crafted more intricate models of cosmic evolution, incorporating the enigmatic influences of dark matter and dark energy, two substances dominating the cosmic landscape. By melding these refined observations with sophisticated models, scientists reached a consensus on the universe's age: 13.8 billion years. This estimate has received validation from various independent measurements, including studies of distant supernovae and the universe's large-scale structure. The age of the universe stands as one of cosmology's most firmly established truths, offering profound insights into the nature of the cosmos. The universe's age speaks volumes about its rich and intricate history, tracing back billions of years to a primordial epoch when the cosmos existed as a compact, searingly hot singularity. It signifies that the stars and galaxies we behold today are the outcome of eons of cosmic evolution, shaped by the relentless tug of gravity and the intricate interplay of matter and energy. The age of the universe serves as a vital clue in our quest to comprehend the cosmos, but it's just one fragment of a broader enigma. Cosmologists grapple with an array of profound inquiries. Why does the universe continue to expand at an accelerating pace? What lies at the heart of dark matter and dark energy? And how do they sculpt the universe's evolution? How did the earliest stars and galaxies come into being? And what characterized the universe in its nascent moments? These questions drive the relentless pursuit of knowledge in the field. One of the captivating aspects of the universe's age is its connection to the fundamental fabric of space and time. According to Einstein's theory of general relativity, space and time intertwine, forming a dynamic four-dimensional construct known as spacetime. This intricate fabric can be bent and twisted by the presence of matter and energy, giving rise to phenomena like gravitational waves and black holes. The age of the universe signifies that spacetime has undergone billions of years of evolution, responding to the cosmic forces by stretching and contorting. It underscores that the very essence of the universe has a narrative, and the structures we observe today emerge from the intricate interplay of spacetime, matter, and energy. While the universe presently expands at an accelerated rate, its ultimate destiny remains uncertain. Some theories propose a perpetual expansion, leading to a cold and desolate cosmos devoid of stellar brilliance. Others speculate on a cosmic contraction, culminating in a cataclysmic event akin to another Big Bang, birthing a new universe. Regardless of the universe's ultimate trajectory, Its age reminds us of the extraordinary moment we inhabit in cosmic history. We exist in an era of perpetual change and evolution, where stars are born, galaxies collide, and the universe continues its inexorable march toward an uncertain future. Studying the universe and its evolution offers profound insights into the cosmos's fundamental nature and our role within it. The age of the universe serves as a gateway to understanding the potential existence of intelligent civilizations beyond our own realm. If life is widespread and the conditions for intelligent life exist elsewhere, there may be civilizations far older and more advanced than ours. Additionally, the universe's age guides our search for extraterrestrial life, informing us about the environments conducive to life's emergence by studying Earth's conditions and biodiversity. Some theories speculate on a multiverse, a vast network of parallel universes with distinct properties and histories. The age of our universe suggests that if a multiverse exists, numerous universes may have emerged over vast epochs, each with its own narrative and destiny. Lastly, contemplating the universe's age evokes a sense of awe and wonder. From the cosmic background radiation lingering since the Big Bang to the intricate ballet of stars and galaxies, the cosmos is a mesmerizing tapestry that humbles and inspires. The universe's age is a remarkable insight with profound implications for our understanding of existence. It sheds light on the universe's origins, the potential for extraterrestrial life, the fabric of reality, and the magnificence of the cosmos. As we continue our cosmic exploration, the age of the universe remains a beacon guiding us in unraveling the universe's mysteries and our place within it. The universe is a vast and complex place filled with phenomena that often defy our understanding. From the enigmatic workings of quantum mechanics to the peculiar nature of black holes, there are countless mysteries waiting to be unraveled. In this documentary, we delve into some of these perplexing aspects of the universe, shedding light on the strange paradoxes that challenge our comprehension. If you're intrigued by the mysteries of the cosmos, consider subscribing to our channel for more captivating content. One astonishing fact is that everything we currently comprehend about the universe represents just a tiny fraction, merely 5%. This portion consists of normal matter, which includes familiar particles like protons, neutrons, and electrons. However, the remaining 95% remains elusive, hidden in the shadows of the cosmos. This vast majority comprises dark matter, 27%, and dark energy, 68%, enigmatic entities that continue to baffle scientists. Dark matter, in particular, is a puzzling substance that behaves unlike any known form of matter. It doesn't interact with light or other electromagnetic radiation, making it invisible to traditional telescopes. Instead, its presence is inferred through its gravitational effects on visible matter, such as galaxies. Despite its prevalence, constituting approximately 85% of all matter in the universe, its composition remains a mystery. Theories abound, ranging from hypothetical particles to exotic phenomena like primordial black holes. Similarly, dark energy adds another layer of complexity to our understanding of the cosmos. This mysterious force is believed to be responsible for the universe's accelerating expansion, but its true nature eludes us. Together, dark matter and dark energy represent the vast unknown, urging scientists to continue their quest for answers amidst the enigmatic depths of space. Dark energy is a speculative type of energy believed to saturate the vast expanse of space, driving the universe's accelerated expansion. Unlike dark matter, which exerts gravitational forces that slow this expansion, dark energy operates oppositely. It exerts a repulsive force, causing the universe to expand even faster. Despite its pivotal role, the precise nature of dark energy remains elusive. Scientists theorize it to be an inherent property of space itself, rather than a tangible form of matter or energy that can be directly observed. Current estimates suggest that dark energy constitutes approximately 68% of the total energy content of the universe. As for the universe's dimensions, our current understanding suggests it encompasses 3 spatial dimensions, length, width, and height, along with 1 dimension of time, culminating in what's known as 4-dimensional spacetime. However, theories such as string theory speculate the existence of additional dimensions, potentially up to 11 in total. These extra dimensions, if they exist, are postulated to be compactified or curled up to minuscule scales beyond our direct observation. Although we cannot perceive them directly, their influence on observable physical phenomena can be inferred. The proposal of these additional dimensions serves a crucial purpose in attempting to unify the mathematical frameworks governing the four fundamental forces of nature: the strong nuclear force, weak nuclear force, electromagnetic force, and gravity. The quest to discern the existence of these higher dimensions poses a tantalizing challenge. Can we detect their presence, or will we remain bound within the confines of our four-dimensional reality indefinitely? The concept of the multiverse theory proposes that our universe is just one among many. This idea, embraced by modern cosmology and physics, suggests the existence of numerous parallel universes, each governed by its own set of unique properties and laws of physics. If this theory holds true, it would revolutionize our understanding of the cosmos and our position within it. One intriguing implication is its potential to elucidate the apparent fine-tuning of our universe to support life, a principle known as the anthropic principle. With countless universes boasting diverse physical laws, the likelihood of at least one nurturing life increases significantly. However, the multiverse theory also prompts profound questions regarding the nature of reality and our perception of what is real. If multiple universes exist with distinct physical laws, do they all possess equal reality, or is our universe privileged in its existence? Now consider time, an enigmatic aspect of our universe that perplexes researchers. Time is conceptualized as a measurable continuum devoid of spatial dimensions. It exhibits an unmistakable flow or direction, seemingly prohibiting backward travel. Are we ensnared in the unidirectional flow of time, forever moving forward? Is time's passage intricately intertwined with the fundamental workings of our universe? These questions delve into the very essence of existence and challenge our comprehension of the universe's fundamental properties. The theory of the Big Bang suggests that time itself began alongside the birth of the universe approximately 13.8 billion years ago. This concept raises the question, does it even make sense to inquire about what existed before this temporal inception? Time, a cornerstone of physics, is commonly defined as the sequential progression of events from the past through the present and into the future. It serves as a fundamental dimension within which events unfold, often depicted as a continuous line or axis. In the realm of physics, time is quantified in units such as seconds, minutes, hours, and years. Moreover, it constitutes a vital element of the space-time continuum, a four-dimensional construct comprising three spatial dimensions and one temporal dimension. The trajectory of time is typically depicted as unidirectional, flowing forward without the possibility of reversal, a phenomenon known as the arrow of time. This arrow finds correlation with the second law of thermodynamics, asserting that entropy, a measure of disorder or randomness within a closed system, tends to increase over time. Despite these conceptual frameworks, the nature of time remains a subject of ongoing exploration and debate across the realms of physics and philosophy. Some theories postulate that time emerges as a consequence of intricate interactions among the universe's fundamental constituents. Conversely, others contend that time is an intrinsic property of the cosmos, analogous to space and matter. Quantum entanglement is a fascinating aspect of particle behavior that may seem to defy our understanding of the natural world. Essentially, it's when two particles become correlated in such a way that the state of one particle is immediately linked to the state of the other, regardless of the physical distance between them. This concept is consistent with the principles of quantum mechanics, even though it might appear to break traditional laws. However, it's crucial to clarify that quantum entanglement doesn't enable faster-than-light communication or disrupt causality. Despite the instantaneous correlation between entangled particles, we can't control or exploit this connection to transmit information at speeds exceeding that of light. This limitation is governed by the no-communication theorem in quantum mechanics, which asserts that such transmission is impossible. So, while quantum entanglement sparks curiosity and seems mysterious, it doesn't actually violate the laws of nature or the principles of causality. As for the questions about using quantum entanglement for instant communication across vast distances or the existence of life beyond Earth, those remain open to exploration. The universe is vast, containing at least 2 trillion galaxies, each potentially hosting numerous stars and planets. This abundance hints at the possibility of other life forms existing beyond our planet. The question of whether we are alone in the vast universe is a fascinating and profound inquiry. Despite the immense number of planets in our galaxy, Earth's seemingly ideal conditions for life suggest that we're not unique. But why haven't we encountered any other life forms? This conundrum is known as the Fermi paradox. There are several theories attempting to explain this paradox. One possibility is that life is indeed rare, requiring specific conditions to emerge. Another is that while life might be common, it struggles to progress to a point where it can communicate across vast distances. Additionally, civilizations may self-destruct before they can explore beyond their home planets. It's also plausible that we simply haven't searched in the right places yet. Understanding this paradox prompts us to ponder the future of humanity. If intelligent civilizations tend to falter before reaching out to the stars, what does that suggest for our own trajectory? Our quest to understand extraterrestrial life is constrained by our current technological capabilities, which are still rather limited. However, advancements in the future may unveil new techniques that could reveal evidence of life beyond Earth. But as we gaze outward into the cosmos, we must acknowledge a fundamental truth. We are not impartial spectators. As humans, we are intricately entwined with the universe we seek to explore. This self-reference poses a profound challenge to our perception. How can we claim neutrality when we are both observers and subjects of observation? This dilemma may skew our understanding, leading to misconceptions about the nature of the universe. The self-reference problem complicates our study of the cosmos. By acknowledging our inherent connection to the universe, we can strive for a more nuanced and accurate interpretation of the cosmos. Our fascination with the universe often leads us to focus on phenomena that directly impact our existence, potentially skewing our perception. But by acknowledging our biases and limitations, we can strive for a more objective and thorough approach to observation and analysis. Why does the universe seem tailor-made for us? This intriguing question has led to speculation about the fundamental constants of our universe, such as the speed of light, which seemingly allow for the existence of life. One explanation is the anthropic principle, suggesting that the universe appears finely tuned for life because we, as observers, exist within it. This concept, also known as the selection effect, implies that if the universe weren't conducive to life, we wouldn't be here to ponder its mysteries. Why is it easier to break things than to mend them? Entropy, a measure of disorder or randomness in a system, plays a crucial role here. In the universe, entropy tends to increase over time, leading to a progression from order to chaos. This explains why it's simple to shatter a window, but impossible to restore it to its original state. What does this mean for the future of the universe? As the universe expands, it heads towards a state of maximum entropy called the heat death, where everything becomes uniformly distributed and energy gradients vanish. This bleak scenario implies a cold, dark, and lifeless cosmos in the distant future. Though the universe isn't entirely closed, receiving energy from stars and other sources, the overall trend is towards greater disorder. However, this process unfolds over an incredibly lengthy timescale, likely spanning trillions of years. Now, can anything escape the clutches of a black hole? These enigmatic objects wield immense gravitational pull, even capturing light itself. While we've observed their effects and directly observed one, what occurs within their infinitely dense centers remains a mystery. Speculations about white holes, which could be the opposites of black holes, expelling matter and even time into our universe, further deepen the intrigue surrounding these cosmic phenomena. In the realm of physics, the grasp of a black hole is unyielding once an object crosses its event horizon, the boundary of no return. Here, the gravitational force is so intense that it distorts both space and time, drawing everything towards the singularity at the core, where conventional laws of physics falter. Yet what unfolds within the heart of a black hole remains an enigma. Our current physics fails to elucidate the conditions prevailing there, theorizing that the matter condenses into an infinitely dense singularity, devoid of volume. As for white holes, their existence remains purely speculative. These hypothetical counterparts to black holes are envisioned at the opposite end of hypothetical wormholes, bridges in space-time connecting distant points. However, empirical evidence supporting their existence, as well as that of wormholes, remains elusive. The cosmos teems with perplexing paradoxes, fueling our pursuit of understanding. As we probe the cosmos' outer reaches and delve into the depths of time, we encounter myriad mysteries. With each revelation, the universe unveils new layers of complexity, propelling us towards greater insights and discoveries. Once limited to our solar system's planets, our understanding has expanded to encompass a vast array of celestial bodies orbiting distant stars. These exoplanets, ranging from rocky terrains to colossal gas giants, offer a rich narrative of cosmic evolution. Originating from stellar remnants like dust and debris, their early histories were likely tumultuous, marked by violent processes. The universe, replete with galaxies, stars, and planets, reveals a diverse tapestry of cosmic landscapes. While our solar system boasts 8 worlds, it's a mere fraction of the countless planets dotting the cosmos. This realization marks a pivotal moment in scientific history, affirming the existence of planetary systems beyond our own. In the Milky Way alone, teeming with 200 billion stars, numerous planetary systems likely await discovery. In 2009, NASA launched the Kepler Space Telescope, embarking on a mission to unveil new planetary realms. Over the years, it has identified over 400 exoplanets, ranging from colossal gas giants dwarfing Jupiter to massive rocky worlds eclipsing Earth's size. Some trace chaotic paths perilously close to their stars, risking obliteration. Yet amidst this diversity, each planet stands as a unique entity. Despite their uniqueness, studying these distant worlds remains a formidable challenge due to their remoteness. Much of our understanding of planetary mechanics derives from our solar system's familiar 8. Here, 2 distinct classes emerge. The rocky quartet of inner planets, Mercury, Venus, Earth, and Mars, and the outer quartet of gas giants, Jupiter, Saturn, Uranus, and Neptune. Each of the 8 planets in our solar system boasts its own distinct identity, shaped by the unique conditions prevalent during the solar system's inception 4.6 billion years ago. The birth of our Sun triggered the dispersal of a vast cloud of gas and dust, serving as the cradle for all 8 planets, regardless of their proximity to the Sun or their composition, be it rocky or gaseous. Despite originating from the same cosmic materials, their formation occurred under vastly contrasting circumstances. Planets nearer to the Sun experienced scorching temperatures, while those farther away endured colder environments. These differing conditions influence the evolution of the planets, akin to ingredients baking into diverse concoctions in an oven. In the early solar system, a blend of silicate, water vapor, hydrogen, and methane pervaded the cosmic dust cloud. As planets formed, their compositions varied, reflecting the nuances of their respective environments. Close to the Sun, where heat was intense, volatile gases evaporated, leaving behind only materials resilient to high temperatures, namely rocks and metals. Consequently, rocky planets like Mercury, Venus, Earth, and Mars emerged in this scorching vicinity. Conversely, planets farther from the Sun underwent a different cooking process, leading to their distinct compositions. The composition of the cloud from which a solar system forms profoundly influences its planetary makeup. In some instances, a dearth of rocky materials may preclude the emergence of Earth-like planets, resulting instead in a prevalence of gas giants or a complete absence of rocky worlds. For rocky planets to form, the cloud must abound with metals and rocks, with subsequent steps involving a reduction in temperature. As the cloud cools, substances with high boiling points begin to condense into solid forms. Minute mineral grains emerge, serving as the rudimentary building blocks of nascent rocky planets. Over time, these grains coalesce through a process known as accretion, gradually accumulating mass. Initially, collisions between dust molecules foster the growth of larger particles, eventually culminating in the formation of rocks. Subsequent collisions between rocks lead to the creation of boulders, which in turn amalgamate into larger formations. Eventually, a critical mass is attained, enabling the nascent planet to exert gravitational pull, attracting nearby debris. Initially, numerous protoplanets vie for dominance within the solar system, potentially numbering in the hundreds. However, most fail to mature into fully fledged planets. A visit to the asteroid belt offers insights into the developmental stages of rocky planets. For instance, asteroid 4 Vesta, measuring a mere 329 miles across, falls short of the spherical shape characteristic of fully formed planets. To achieve this roundness, a growing planet must surpass a diameter of 500 miles, indicating the threshold at which gravitational forces crush it into a spherical form. Upon reaching a critical size, a young planet transitions from its irregular shape to a more spherical form. However, each collision with other celestial bodies generates significant heat, gradually melting the planet's surface. Amidst this turmoil, gravity plays a pivotal role, segregating heavier materials towards the core while lighter elements rise to form a crust. Yet this phase marks a tumultuous period, a time of chaos and upheaval that will ultimately determine a planet's fate. Originating from the same primordial cloud of dust and gas, each planet emerges with its unique characteristics, shaped by a combination of chance occurrences and the laws of physics and chemistry. Approximately 4.5 billion years ago, our solar system was a battleground, teeming with around 100 fledgling planets engaged in a frenzied demolition derby. Collisions were rampant, with many occurring during the final stages of planetary growth. As these collisions reshaped the planetary landscape, some bodies grew at the expense of others, gradually increasing in size. The larger planets began to gravitationally attract smaller bodies, leading to intense bombardment and the accumulation of space debris on their surfaces. When the chaos subsided, only 4 rocky planets remained, each bearing the scars of its tumultuous past. These formative experiences have endowed each planet with distinct characteristics. Mars, a desolate frozen wasteland; Earth, a vibrant hub of liquid water; Venus, a fiery realm dominated by volcanoes; and Mercury, a diminutive, scorched world devoid of atmosphere. Due to significant collisions in the past, celestial bodies like Mercury and Earth have undergone dramatic transformations. For instance, Mercury, with its thin crust and high density, suggests it could have been larger in the past. A collision at an angle likely stripped away its lighter crust, leaving behind the dense core we observe today. Similarly, Earth experienced a violent impact in its early history, resulting in the detachment of its mantle, which then coalesced to form the Moon. Mars also bears evidence of past collisions, with its northern hemisphere exhibiting thinner crust compared to the southern hemisphere. One hypothesis suggests a massive impact early in Mars's history removed a significant portion of its crust, leading to subsequent crustal buildup in the southern region. These collisions not only reduced the population of nascent planets, but also contributed additional materials to surviving celestial bodies. The composition of these materials played a crucial role in planetary development. Metal-rich chunks tended to sink towards the core during collisions, while lighter or icy components formed the crust. The rocky planets near the Sun, including Earth, were primarily composed of a solid iron core surrounded by liquid iron and molten rock, topped with a surface crust. Despite their shared origins, each rocky planet exhibits distinct characteristics in size and destiny. Although space appears empty, it's teeming with particles ejected from the Sun. The Sun's strong magnetic fields create solar winds composed of highly charged particles which shoot into space when these fields interact. Astronauts can perceive this phenomenon as a faint glow when they close their eyes due to energetic particles interacting with the fluid in their eyes, creating occasional flashes of light. Solar wind poses a significant threat to astronauts as exposure to higher levels could be fatal. An example of this danger occurred during the Apollo program when a solar explosion occurred between 2 moon missions. Had astronauts been present, they would have faced potentially lethal levels of radiation. However, the threat of solar radiation is mitigated here on Earth due to our protective magnetic field. This invisible shield, generated from the Earth's core, shields us from the harmful effects of the solar wind. As a result, while space is fraught with radiation hazards, we are relatively safe from them on our home planet. I'll leave it at that. Thank you so much for watching another documentary. Be sure to subscribe if you enjoy these astronomy documentaries. And with that being said, take care. End. Exploring the universe's finale blends cosmic marvels with deep thinking, intriguing both scientists and philosophers similarly. As we ponder the end of the universe, we dive into a realm where numbers and scientific ideas mix with questions about existence. Come along as we explore this captivating journey into the universe's ultimate fate. One prominent theory, backed by extensive scientific evidence, emerges as a frontrunner in this cosmic puzzle: the Big Freeze, also known as the heat death of the universe. This theory finds its roots in thermodynamics, a branch of physics dealing with heat, temperature, energy, and work. The Big Freeze scenario revolves around the second law of thermodynamics, which states that in an isolated system like the universe, entropy, a measure of disorder or randomness, tends to increase over time. According to this theory, as the universe expands, driven by the enigmatic force of dark energy, it gradually cools down as its energy disperses across a growing volume. Eventually, all stars will exhaust their nuclear fuel, fading into darkness. Galaxies will drift apart, and over immense timescales, black holes will evaporate. In the distant future, the universe will reach a state of maximum entropy, where there's no significant energy exchange, rendering it uniformly cold and dark. This Big Freeze scenario is the most probable outcome according to our current understanding of cosmology, particularly based on measurements of cosmic microwave background radiation, the lingering light from the Big Bang, and observations of the universe's accelerating expansion. These observations suggest that the universe is flat and will likely keep expanding indefinitely. While this paints a bleak picture of the universe's far future, it's important to note that this isn't something imminent, but rather something that will unfold over an incredibly vast span of time beyond our grasp. We're talking about timescales in the trillions of years, far surpassing the universe's current age of about 13.8 billion years. Our understanding of the universe's fate has evolved significantly over the years, thanks to advancements in technology, astrophysics, and theoretical models. This journey began in the early 20th century with astronomers like Edwin Hubble, whose observation of the redshift in light from distant galaxies provided the first solid evidence of the universe's expansion. This discovery was pivotal, shifting scientific consensus away from the belief in a static universe. In the following decades, scientists wrestled with the implications of this expanding universe. Early models suggested that if the gravitational pull of all matter was strong enough, it might eventually halt expansion and lead to a big crunch, where the universe collapses back in on itself. This theory suggested a cyclic view of the universe, where each collapse, or crunch, would be followed by another Big Bang, and the cycle would repeat. However, in the late 1990s, observations of Type Ia supernovae, extremely bright and distant stellar explosions, brought surprising new evidence. These observations not only confirmed that the universe is expanding, but also revealed that this expansion is speeding up. This acceleration hinted at the presence of a mysterious force called dark energy, which seems to oppose gravity, causing the universe to expand faster and faster. The discovery of dark energy marked a significant shift, leading to the prevailing theory of the Big Freeze, or heat death. According to this theory, the universe will keep expanding endlessly. Over trillions of years, energy will spread out more and more, causing the universe to gradually cool and dim. Additionally, modern cosmology has been transformed by detailed mapping of the cosmic microwave background radiation. This leftover radiation from the Big Bang offers crucial insights into the universe's early conditions and its subsequent evolution. Studies of the CMB support the notion of a flat and accelerating universe, supporting the Big Freeze idea. On the other hand, the Big Crunch theory offers a captivating and dramatic scenario for the universe's ultimate fate. It presents a counterpoint to perpetual expansion, rooted in the principles of gravity. According to the Big Crunch theory, the universe's expansion, initiated by the Big Bang, will eventually slow and reverse due to the gravitational attraction of all matter and energy. This would result in a gradual collapse of the universe, pulling galaxies, stars, and eventually all matter back toward a singular point. This theory draws upon principles from general relativity and posits that the universe's destiny is closely linked to its density. If the universe's density is high enough, all the gravity from stars, galaxies, and other cosmic objects could eventually outweigh the force pushing them apart. This would cause the universe to stop expanding and start collapsing back in on itself. As it contracts, temperatures would skyrocket, potentially undoing the effects of the Big Bang in a kind of cosmic rewind. The collapse, known as the Big Crunch, would end in a state of extreme density and heat, similar to the universe's early moments after the Big Bang. Some theories even suggest that this collapse could trigger another Big Bang, proposing a cycle where each collapse is followed by a new expansion phase. However, recent astronomical observations have cast doubt on the Big Crunch theory. The discovery of the universe's accelerating expansion implies that the influence of dark energy outweighs the gravitational pull of all matter. This suggests that the universe might keep expanding forever, making the Big Crunch scenario less likely according to current cosmological models. The Big Rip and the Big Crunch are two different theoretical scenarios for the universe's end, each with vastly different processes and outcomes. The Big Crunch involves the universe's gradual collapse, driven by the gravitational pull of matter and energy. If you're still watching, please like the video and turn on notifications for the channel so you don't miss our weekly documentaries. Moving on. As the collapse progresses, everything in the universe gets compressed into a single, incredibly dense point. This theory relies on the idea that the universe's density is high enough to counteract its expansion, aligning with principles from general relativity. However, it has become less favored due to observations indicating the universe's accelerating expansion. On the opposite end of the spectrum, we have the Big Rip theory, which suggests that the universe's expansion not only persists, but speeds up indefinitely due to dark energy. Here, dark energy eventually becomes so dominant that it overwhelms all other forces, including gravity and electromagnetic forces that hold everything together, from galaxies down to atoms. As the universe rapidly expands, it reaches a point where these fundamental forces can't keep structures intact anymore. Galaxies would tear apart, followed by the breakup of individual star systems, planets, and eventually the very essence of matter itself. The Big Rip ends with the universe torn apart at its most basic level, resulting in a sparse, cold, and dark state with particles scattered far apart. The main contrast between the two theories lies in their driving forces. The Big Crunch is pushed by gravity, leading to a collapse, while the Big Rip is propelled by a relentless acceleration of the universe's expansion due to dark energy. Furthermore, the timelines for these events differ greatly. The Big Rip would happen relatively quickly once it gains momentum, unlike the Big Crunch, which would unfold over a longer period. Both theories showcase the intricate and ever-changing nature of the universe, offering different viewpoints on how its story might conclude. While current observations hint that a Big Rip might be more plausible than a Big Crunch, these are still speculative ideas in cosmology. Now let's talk about the concept of heat death, also known as the Big Freeze. This idea is rooted in thermodynamics, specifically the second law, which says that the total disorder or entropy of a closed system can't decrease over time. In the universe's context, this means that entropy keeps rising until it reaches a peak. The heat death scenario envisions a future where the universe expands so much that all energy is evenly spread out. This uniform energy distribution results in no thermodynamic free energy, meaning no more useful work can be extracted from the system. In simpler terms, it's like a battery fully drained of power and unable to recharge. In this scenario, stars will run out of fuel and stop shining, leaving behind remnants like white dwarfs, neutron stars, and black holes. Eventually, even these remnants will fade away, with black holes evaporating due to Hawking radiation. Galaxies will drift apart, and the universe will become vast, cold, and dark. Temperature differences, which drive energetic processes, will disappear. Without these variations, no energy transfer can happen, leading the universe to a state of maximum disorder and equilibrium. At this point, all known physical processes would stop. The heat death scenario is seen as the most probable outcome based on current cosmological models, which consider the universe's observed accelerated expansion. This expansion, fueled by dark energy, suggests that the universe will keep growing, eventually dispersing all matter and energy. Black holes, mysterious and powerful cosmic entities, are key players in theories about the universe's end. Their unique characteristics offer insights into the universe's long-term fate. In the Big Crunch theory, black holes could hasten the universe's collapse by exerting significant gravitational pull. They might merge and grow larger, accelerating the universe's contraction towards a denser state. However, in the heat death scenario, black holes mark one of the universe's final stages. After stars die out and galaxies disperse, black holes remain. Over vast timespans, even black holes evaporate, emitting Hawking radiation. This process is slow but inevitable, contributing to the eventual dispersal of all matter and energy. As black holes evaporate, they gradually lose mass until they disappear entirely. This slow evaporation could be one of the last events in the heat death scenario for the universe. As black holes emit Hawking radiation, they contribute to the universe's increasing disorder. When the last black hole vanishes, the universe would be left extremely cold, with almost no energy and lacking any significant structure, a stark contrast to its fiery and dynamic beginning. Studying black holes and their characteristics like event horizons and singularities helps us understand the fundamental nature of space-time and quantum mechanics. These understandings are crucial for developing a more complete theory of the universe's fate, especially in bridging the gap between general relativity and quantum physics. Dark energy, a mysterious force captivating scientists and the public alike, plays a vital role in determining the universe's future. It's a type of energy present throughout space that speeds up the universe's expansion. Scientists first inferred its existence from observations of distant Type Ia supernovae in the late 1990s. These observations showed that the universe's expansion rate is actually increasing over time, contrary to previous beliefs. Known forces of gravity acting on visible matter alone couldn't explain this acceleration, leading to the hypothesis of dark energy as an unknown repulsive force. Dark energy is one of the biggest mysteries in modern cosmology. It's invisible and doesn't interact with light, making it super tricky to spot directly. Scientists have come up with different theories to explain it, from ideas like Albert Einstein's cosmological constant to more complex concepts involving new fields and particles. Dark energy is super important for the future of the universe. If it keeps on being the main source of energy, like current observations suggest, it's going to have a huge impact on what happens next. Dark energy's push is making the universe expand faster and faster, leading to possibilities like the Big Rip or the heat death. In the Big Rip scenario, this push gets so strong that it tears everything apart: galaxies, stars, planets, even atoms. In the heat death scenario, the ongoing expansion makes the universe colder and emptier as stars and galaxies move farther away and lose their energy. With dark energy calling the shots, the universe might just keep on expanding forever, getting bigger, colder, and lonelier as time goes on. This marks a shift from earlier ideas like the Big Crunch, where the universe's expansion would eventually halt and reverse. But how do we measure the universe's expansion rate? Measuring this rate, known as the Hubble constant, is a fascinating process that involves advanced technology and keen astronomical observations. One primary method involves looking at the redshift of distant galaxies. As galaxies move away from us due to the universe's expansion, the light they emit shifts towards the red end of the spectrum. By measuring this redshift, astronomers can figure out how fast these galaxies are moving away from us. To determine the universe's expansion rate, astronomers use specific objects called standard candles. These are objects like Type Ia supernovae, which explode with a consistent brightness. By observing how bright these supernovae appear from Earth, scientists can estimate their distance. The farther they are, the fainter they appear. Similarly, Cepheid variables, a type of star with a predictable brightness pattern, serve the same purpose. By measuring these distances and matching them with the speed of galaxies' movement, astronomers can work out the universe's expansion rate. Another method involves studying the cosmic microwave background, the leftover radiation from the Big Bang. By analyzing the CMB's small temperature changes, astronomers can figure out various aspects of the universe, including its expansion rate. This approach gives us a peek into the universe's early days, which offers a different angle from studying far-off galaxies today. Also, baryon acoustic oscillations, BAO, regular periodic patterns in how visible matter is spread out, come into play. By examining these patterns and the universe's large-scale structure, astronomers can figure out how quickly the universe was growing at different times in its history. There's also a newer method called gravitational lensing that helps with these measurements. This happens when a massive object, like a cluster of galaxies, bends the light from things behind it because of its gravity. How much the light bends can tell us about how fast the universe is expanding based on the universe's shape, which is influenced by its expansion rate. Each method has its own complexities and limits. Interestingly, they sometimes give slightly different answers for the Hubble constant, which has caused a bit of confusion in cosmology called the Hubble tension. Quick reminder to subscribe if you haven't already, so you can keep up with our future astronomy documentaries. Thank you so much. Now let's talk about dark matter's role in the universe's end. Dark matter, a mysterious but crucial part of the universe, is key in theories about how the universe will end. Even though we can't see dark matter and it doesn't give off or absorb light, we know it's there because of its gravity's effects on things we can see, like stars and galaxies. Understanding dark matter is vital for predicting what will happen in the end. In the big picture of the universe's fate, dark matter's main influence comes from its gravity. This mysterious stuff makes up about 27% of the universe's total mass and energy, way more than the regular stuff we see, like stars and planets. Its gravity has been super important in shaping how the universe is structured, pulling stuff together to form galaxies and groups of galaxies. In scenarios like the Big Crunch, dark matter's gravity could be a big deal. If dark matter's pull is strong enough to counteract the universe's expansion caused by dark energy, it could make the expansion stop and even reverse. In such a situation, the universe would stop getting bigger and start getting smaller, eventually squeezing all matter into one tiny, super-dense point. But recent observations, especially of how the universe's expansion is speeding up, suggest that dark energy's push is stronger than dark matter's pull. This makes the Big Crunch scenario less likely for now. In the heat death idea, dark matter still plays a role, but it's not as active. As the universe stretches out and cools down, dark matter, just like regular stuff, spreads out more thinly. Its gravitational pull weakens as galaxies and groups of galaxies move farther apart. In a universe headed for heat death, dark matter sticks around, but its power to shape how the universe looks and works fades away over time. Understanding dark matter's part in the universe's end helps us grasp how the universe changes and grows over time. It's like a cosmic support structure, shaping how galaxies and groups of galaxies form and move. But because dark matter is so mysterious, we're still not sure about a lot of its properties and what it means for the universe's long-term future. Now, let's look into thermodynamics a bit. Thermodynamics is a branch of physics all about heat, temperature, and how they're connected to energy and work. It's really important in figuring out what happens to the universe in the end. The laws of thermodynamics, especially the second law, are key to theories about how the universe will keep changing until it reaches its final state. The second law says that in a closed system, like the whole universe, disorder or randomness always increases over time. Applying this to the universe means that its disorder keeps going up until it hits a maximum. This growing disorder has a big effect on what happens next. As disorder increases, the energy we can use to do things goes down, until we reach a point where there's no more significant energy changes possible. We call this heat death or the big freeze. In this state, the universe hits a kind of energy balance, with energy spread out evenly everywhere and no more heat moving between different parts of the universe. This even spread means that all processes relying on energy differences like star burning, structure formation, and even life would stop. The idea of increasing disorder also links to how the universe expands. As the universe gets bigger, matter and energy spread out more, leading to more disorder. If the universe keeps expanding forever, as suggested by our current understanding of dark energy, this spreading out would keep increasing disorder, eventually leading to heat death. Additionally, the second law of thermodynamics might affect the flow of time. In our everyday experience, time moves in one direction from past to future, just like entropy increases. Some physicists think the growing disorder of the universe might be connected to how we see time moving. So, if we know all this, what stops us from predicting how the universe will end? When trying to predict the universe's fate, our models run into several limits because of the huge complexity of space and our current scientific knowledge. These limits are crucial to recognize because they show where our understanding still needs work. One big limit is our limited grasp of dark energy and dark matter. These mysterious parts of the universe are key to how it changes, but we don't know much about them. Dark energy, which speeds up the universe's expansion, can't be seen directly, and we figure out its properties from its gravity's effects. This means our models are missing some pieces as we're working with an incomplete picture of what the universe is made of. Another challenge comes from measuring distances and phenomena in space. The universe is incredibly huge, and figuring out distances, speeds, and other space stuff across such massive scales is really tough and can have mistakes. For instance, when we use things like type Ia supernovae as standard candles to measure distances, there's a whole bunch of steps involved, each with potential for mistakes. The Hubble tension is a big example of these measurement issues. It's about how we get different values for the Hubble constant, which shows how fast the universe is expanding when we look at early universe stuff compared to stuff nearby. This difference suggests there might be things we don't know about affecting the universe's expansion, showing our models have limits. Also, our big theories like general relativity and quantum mechanics have their own limits. These are the basic ideas of physics, but they haven't been fully put together yet, especially in really extreme situations like black holes or the start of the universe. Since we don't have all the answers, our predictions might not be right in these extreme cases. Lastly, science is always changing. What we know about the universe has changed a lot over time and will keep changing. New discoveries, better technology, and new theories could totally change how we see the universe. How does entropy tie into the universe's end? Entropy, a concept from thermodynamics, is key to understanding how the universe will eventually fade away. Simply put, entropy measures how messy or disorganized things are in a system. The second law of thermodynamics says that in a closed system, like the universe, entropy always goes up over time. This steady rise in entropy has big implications for the universe's future. As the universe changes, it naturally heads towards a state where entropy is at its highest. This means all the energy in the universe gets spread out evenly. In a universe with maximum entropy, energy is everywhere, but there are no differences in energy to drive changes or do work. This state is often called heat death or the big freeze. In this scenario, stars, which rely on energy differences, like when hydrogen turns into helium through fusion, would run out of fuel and stop shining. Over billions and billions of years, all the leftovers from stars would cool down, black holes would vanish because of Hawking radiation, and the universe would become a big, cold, dark place with hardly any structures like galaxies or stars. This idea of increasing entropy leading to heat death is different from an older idea in cosmology called the Big Crunch, where the universe's expansion would stop and then reverse, ending in a collapse back to a single point. The heat death idea, based on the second law of thermodynamics, suggests a slow, steady decline into disorder and balance. It's worth noting that the timeline for the universe to reach maximum entropy is incredibly long, much longer than the universe's current age of 13.8 billion years. Understanding entropy and its role in the universe's end not only gives us a glimpse into the distant future of the cosmos, but also highlights the fundamental laws of physics guiding its journey from the Big Bang to now and beyond. What are some other ideas about how the universe might end? Exploring these alternative theories takes us into the realm of creative and advanced cosmology. While these ideas are more speculative, they offer fascinating possibilities for the universe's future. One idea is the cyclic or oscillating universe theory. This suggests that the universe goes through endless cycles of expansion and contraction. Picture the universe expanding from a big bang, stretching out for billions of years, then contracting back into a dense state only to explode outward again. This rhythmic pattern challenges our usual understanding of how the universe unfolds over time. Another captivating concept is the multiverse theory. This broadens our view beyond just our universe, proposing the existence of many, maybe even infinite universes. Each of these universes could have its own laws of physics and unique features. In this context, the fate of our universe might be just a small part of a vast, ever-changing multiverse. Then there's the Big Bounce idea, a variation of the cyclic universe concept. Instead of a series of big bangs and big crunches, the Big Bounce suggests a universe bouncing back from a highly compressed state, rebounding into expansion instead of collapsing into a singularity. This model often brings in elements from quantum theory and offers a smoother transition from one phase to another. Lastly, there's the theory of vacuum decay, or the false vacuum collapse. It presents a dramatic and sudden way for the universe to end. In this theory, our universe exists in a false, unstable vacuum state. Suddenly, it could transition to a true, more stable vacuum, rewriting the laws of physics and drastically changing the universe's structure. This hypothetical event would spread at the speed of light, creating a new type of universe in its wake. How do faraway galaxies give us clues about the universe's future? Distant galaxies serve as cosmic guides, helping us see into the universe's future. When we study these galaxies, we're actually looking back in time because of how far away they are. This makes them incredibly useful for understanding not only the universe's past, but also what might happen down the road. One important way faraway galaxies inform us about the future is through their movement, particularly something called redshift. As galaxies move away from us, the light they give off gets stretched, making it look more red. This redshift helps us figure out how fast the universe is expanding. By measuring the redshift of different galaxies at various distances, astronomers can see how the universe's expansion rate has changed over time. This information is crucial for predicting whether the universe will keep expanding forever, leading to something like the Big Freeze, or if it might take a different turn. Another important aspect is how distant galaxies help us understand dark energy. This mysterious force, making up around 68% of the universe, is pushing its expansion faster. By watching distant galaxies move away from each other, scientists can learn more about dark energy. Studying its past effects on the universe's expansion helps cosmologists make educated guesses about its future influence. Distant galaxies also give us clues about the evolution of cosmic structures. By watching galaxies form and interact far away, we learn about how galaxies live and change, including when they merge. This knowledge helps us predict what might happen to galaxy clusters in the long term, including our own local group. Also, by looking at the light from these galaxies, astronomers learn about stars' lives and the elements in the universe. This tells us about how stars will evolve and how the universe's element mix might change over billions of years. The cosmic microwave background radiation is vital in cosmology, especially when we talk about the universe's end. This radiation is like a snapshot of the universe's birth, the Big Bang. It's a critical piece of evidence for understanding how the universe started and grew. The CMB shows us what the universe looked like when it was only 380,000 years old. At that point, it had cooled enough for electrons and protons to form hydrogen atoms, making the universe transparent to radiation for the first time. Even though the radiation has cooled to microwaves due to the universe expanding, it still holds a lot of information. One of the big jobs of the CMB is helping us measure the Hubble constant. This constant tells us how fast the universe is expanding. By studying the CMB data, scientists figure out how fast the universe expanded at different times. This data is super important for testing and refining ideas about the universe's future, like the Big Freeze or Big Rip scenarios. The CMB also tells us about the universe's shape and what it's made of. By looking at temperature and density differences in the CMB, astronomers calculate how curved the universe is and estimate how much ordinary matter, and dark energy there is. This helps us predict how these things will affect the universe's expansion and what might happen in the end. The discovery of the cosmic microwave background was a significant milestone in confirming the Big Bang theory, which forms the basis for many cosmological ideas about how the universe might eventually end. Essentially, the CMB tells us that the universe started out hot and dense, providing a crucial starting point for understanding its past and potential future. Studying the CMB in detail also helps to narrow down the possibilities for alternative theories about the universe's fate. Any viable theory must match up with what we observe in the CMB data. For example, theories suggesting a cyclic or oscillating universe need to explain why the CMB appears uniform and has specific properties that we see today. As for whether we can simulate or model the universe's end, it's a challenging but active area of research for astrophysicists and cosmologists. They're using cutting-edge technology and complex math to try to understand and predict how the universe might evolve and eventually come to an end. To simulate the universe's end, scientists need to accurately model the various forces at work, including gravity, dark matter, and dark energy. They do this by running sophisticated computer simulations that incorporate equations from general relativity. These simulations help visualize different scenarios, such as the Big Crunch, where the universe collapses back in on itself, or the Big Freeze, where it continues expanding indefinitely. For example, in simulations of the Big Crunch, researchers focus on how gravity might eventually overcome the expansion caused by dark energy. On the other hand, simulations of the Big Freeze project the current rate of expansion into the future, considering how dark energy will continue to push galaxies apart until all activity stops. Furthermore, scientists use these models to delve into the mysteries of dark matter and dark energy, two of the universe's most enigmatic components. By adjusting how these elements behave in their models, researchers can explore different outcomes and grasp how much the universe's fate hinges on them. While these simulations offer valuable insights, they're limited by our current grasp of the universe's laws and components. The accuracy of these models relies heavily on the data and theories they're built upon. For instance, any shifts in our understanding of dark energy or the discovery of new cosmic phenomena could significantly change the predicted results. Additionally, the immense time spans involved in cosmic evolution pose a challenge. These simulations often span billions to trillions of years, well beyond human lifetimes, making it hard to test and confirm predictions, keeping them largely in the realm of theoretical astrophysics. How does quantum mechanics affect our understanding of the universe's end? Quantum mechanics, the field of physics dealing with the tiniest particles, has profound implications for how we view the universe's ultimate fate. It introduces concepts that fundamentally alter scientists' perspectives on the cosmos, especially concerning its final state. One critical aspect where quantum mechanics plays a role is in the realm of black holes. Quantum theories, like those involving Hawking radiation, propose that black holes emit radiation and may gradually lose mass over immense periods. This concept suggests a mechanism by which even the most massive and long-lasting objects in the universe, black holes, could eventually vanish. In the context of the universe's end, this process could be significant, particularly in scenarios like the heat death, where black holes may be among the last structures remaining. Additionally, quantum mechanics introduces the idea of quantum fluctuations, small random changes in energy at a microscopic level. In a universe moving towards maximum disorder, as in the proposed heat death scenario, these fluctuations could have intriguing implications. Over unfathomably long periods, tiny fluctuations at the quantum level could potentially give rise to new particle arrangements or even spawn entirely new universes, as some theories propose. This introduces a layer of unpredictability and complexity to our grasp of how the universe might eventually end. Another area where quantum mechanics plays a crucial role is in our investigation of dark matter and dark energy. Despite their critical role in shaping the universe's destiny, we still don't fully comprehend their nature. Quantum theories offer potential insights into the characteristics of these elusive components, influencing our models of the universe's evolution. Furthermore, reconciling quantum mechanics with general relativity stands as one of the greatest puzzles in modern physics. This reconciliation holds the key to understanding extreme cosmic conditions, such as those prevailing in the early universe or within black holes. Achieving this synthesis could profoundly alter our predictions regarding the universe's fate, particularly concerning scenarios involving cosmic collapse or rebirth. What role does time play in theories about the universe's end? Time occupies a central and fascinating position in our contemplation of the universe's ultimate fate. In simple terms, time measures the progression and change from one state to another. In cosmology, grasping the nature of time is crucial for unraveling how the universe might unfold and eventually meet its end. Firstly, the vast temporal scales involved in these theories are mind-boggling. We're talking about billions to trillions of years into the future, surpassing all known human history, or even the universe's current age, estimated at around 13.8 billion years. For example, the concept of the heat death of the universe, where all cosmic activity ceases due to maximum entropy, is projected to occur over a time frame so immense that it dwarfs all known temporal measures. Time also intertwines with the notion of entropy, a fundamental concept in thermodynamics. The second law of thermodynamics tells us that entropy tends to increase in an isolated system over time, implying that as time advances, the universe should become increasingly disordered. This gradual increase in disorder guides our predictions about the universe's progression towards a state of equilibrium, where significant energy exchanges cease, ultimately leading to the heat death scenario. Moreover, in cosmology, time isn't just a linear progression from past to future. Theoretical models exploring the universe's fate often venture into the concept of time as a dimension entwined with the very fabric of space. In these models, the geometry and destiny of the universe are intimately connected with our understanding of time's structure and dynamics. For instance, in theories suggesting a cyclic universe, time might be viewed as a continuous loop, with each cycle of the universe's birth, expansion, and demise repeating endlessly. Additionally, time is crucial for understanding how cosmic structures evolve and decay. Processes like the lifespan of stars, the creation and disintegration of galaxies, and phenomena such as the gradual evaporation of black holes via Hawking radiation all unfold over time and contribute to the overall trajectory of the universe toward its eventual end. Now, how might the discovery of new particles change our forecasts? The detection of new particles could significantly shake up our predictions about the universe's fate, providing fresh perspectives and potentially reshaping our understanding of fundamental physics. Particle physics, the field that explores the tiniest building blocks of matter, has a track record of transforming our comprehension of the universe, and any new discoveries would likely continue this trend. Identifying new particles could yield crucial insights into dark matter, which makes up around 27% of the universe but remains one of its most enigmatic aspects. Currently, we can only infer the existence of dark matter through its gravitational effects. The discovery of particles that could be linked to dark matter would open up a new frontier in physics, allowing us to delve deeper into how this mysterious substance influences the universe's structure and evolution. This could, in turn, affect our theories about the universe's end, particularly if dark matter behaves differently than what we currently understand. Furthermore, new particle discoveries could illuminate dark energy, the perplexing force fueling the universe's accelerating expansion. Understanding the particle properties of dark energy, if it indeed has any, could be pivotal in foreseeing the universe's destiny. For example, if dark energy were found to vary over time, it might imply changes in the universe's expansion, potentially leading to scenarios like the Big Rip, or even a reversal to a Big Crunch. Another area where new particles could impact our predictions is in the realm of quantum mechanics and its interplay with general relativity. The discovery of particles with unexpected gravitational interactions or insights into quantum gravity could aid in formulating a theory of quantum gravity, a long-standing quest in physics. This could completely change how we understand extreme cosmic conditions, like what happens inside black holes or at the universe's beginning, and could influence our ideas about how the universe might eventually end. Moreover, discovering new particles might challenge or refine the standard model of particle physics, our best current explanation for the fundamental forces and particles in the universe. Any adjustments to this model could have big effects, reshaping our understanding of the basic building blocks of the universe and how they interact. The philosophical implications of the universe's end are as deep as they are diverse, touching on questions that humans have pondered for centuries. The notion that the universe could one day reach a definite end challenges our basic understanding of existence, time, and our role in the grand scheme of things. Firstly, thinking about the end of the universe makes us confront the idea of impermanence on a cosmic scale. For many people, the thought that the entire universe, including all its galaxies, stars, and even the atoms composing our bodies, might one day cease to exist or change beyond recognition is a humbling reminder of life's temporary nature. This can lead us to wonder about the value and meaning of our actions, civilizations, and even our pursuit of knowledge when faced with the vast, indifferent expanse of space. Additionally, theories about the universe's end also make us think deeply about time. If the universe is moving toward a state like the heat death, where everything stops changing, it raises questions about time itself. Is time an everlasting, continuous stream, or does it have a beginning and an end? These questions intersect with both philosophical and scientific debates about the nature of reality and how we perceive it. The idea of scenarios like the cyclic universe, where the universe goes through an endless cycle of expansions and contractions, also sparks philosophical reflections on eternity and the idea of things repeating indefinitely. This concept, suggesting that the universe and all its events could endlessly recur, prompts discussions about determinism, free will, and what makes human experience unique. Additionally, examining how the universe might eventually end delves into deep questions about existence. Recognizing that one day everything in the universe could cease to exist can stir up feelings of existential anxiety. However, it can also prompt a sense of freedom or a push to find purpose in the present moment. It encourages us to think about what it means to be alive in a universe that has limits and is constantly changing. Lastly, pondering the end of the universe urges us to reconsider our ideas about progress and our advancements in technology and science. It challenges us to think about humanity's role in the vast cosmos and prompts us to reflect on the impact we leave behind, not only on Earth, but also within the broader story of the universe. How have various cultures viewed the end of the universe? Throughout history, different cultures have offered their own unique perspectives on how the universe might reach its end, reflecting a diverse array of cosmological myths, religious beliefs, and philosophical concepts. These cultural narratives often blend science, philosophy, and spirituality, providing varied outlooks on the universe's ultimate fate. In Western traditions, heavily influenced by Judeo-Christian ideas, the end of the universe is often depicted as an apocalyptic event. This perspective, found in texts like the Book of Revelation, portrays a final judgment and transformation rather than a literal end of the cosmos. It emphasizes moral and spiritual conclusions rather than scientific details. Conversely, many Eastern philosophies and religions, such as Hinduism and Buddhism, propose a cyclical view of the universe. For example, in Hindu cosmology, the universe experiences repetitive cycles of creation, preservation, and destruction, known as Mahayuga. This cyclic process holds not only physical significance but also carries spiritual meaning, symbolizing the eternal rhythms of birth, life, and rebirth. Indigenous cultures across the globe also offer their own interpretations. Some Native American traditions, for instance, speak of a sequence of worlds or ages, each concluding with a transition to the next through various forms of renewal or destruction. These stories often highlight the importance of living in harmony with nature and recognizing the interconnectedness of all living beings, portraying the end of the universe as a natural and sacred part of a larger cycle. For instance, in Norse mythology, there's the concept of Ragnarok, a series of events that include a great battle resulting in the death of major gods and a world flood. After these cataclysms, it's prophesied that the world will emerge anew and fertile, with surviving gods reuniting and two humans repopulating the Earth. In modern times, as our scientific understanding of the universe has grown, these cultural tales have sometimes intertwined with scientific theories. For example, the notion of an expanding universe heading towards a cold, dark end may resonate with both apocalyptic and cyclical beliefs, seen as either the final state of entropy or just one phase in an ongoing cycle of cosmic events. Each of these cultural viewpoints not only reflects ideas about the end of the universe, but also deeper values and insights about life, existence, and the nature of change and continuity. They show how humans have long pondered not only the physical aspects of the cosmos, but also its metaphysical and spiritual dimensions, from its beginning to its end. Now let's delve into an intriguing hypothesis. The vacuum decay hypothesis is a captivating and somewhat unsettling idea in the realms of cosmology and theoretical physics. It proposes a scenario where the universe doesn't end with a bang or a whimper, but with a bubble. This hypothesis revolves around the notion of a false vacuum, a tentative or unstable state of space containing potential energy. In this scenario, our current universe exists in a false vacuum, a temporary and unstable condition that could decay into a more stable state, known as the true vacuum. This decay could be triggered by a random quantum fluctuation, creating a bubble of this true vacuum. What's particularly unsettling about this hypothesis is what happens next. This bubble would expand at the speed of light, altering anything it touches at a fundamental level. The laws of physics as we know them might completely change inside this bubble. Everything we're familiar with, galaxies, stars, planets, and even the basic components of matter, could be destroyed or drastically transformed as the bubble engulfs them. The vacuum decay theory is purely theoretical and not something we can expect to happen anytime soon. It's based on ideas from quantum mechanics and quantum field theory, which study how the universe behaves at its smallest levels. The theory suggests that what we think of as empty space might actually be filled with invisible energy fields. One interesting aspect is that this process could occur suddenly and without warning because it would spread at the speed of light. We wouldn't see it coming. But it's important to understand that this theory is just one of many speculative ideas about how the universe might eventually end. Can advancements in technology help us understand the universe's end better? Absolutely. Technological progress has always been crucial in expanding our knowledge of the cosmos, and it's key to uncovering new insights into how the universe might meet its end. As we develop better tools and computer models, our ability to observe, measure, and understand cosmic events improves, bringing us closer to answering some of the universe's biggest questions. One area where technology is making a big difference is in observational astronomy. New telescopes, both on the ground and in space, allow astronomers to see distant cosmic phenomena more clearly than ever before. For example, telescopes like the James Webb Space Telescope can peer deeper into space, potentially revealing new information about the early universe that could help us predict its end. Alongside observational tools, advances in computing are also crucial. Supercomputers can now process vast amounts of data and run complex simulations faster than ever. These simulations let scientists model different scenarios for the universe's end, from the Big Freeze to the Big Rip, with incredible detail. By tweaking variables in these models, researchers can explore a wide range of possible outcomes. Furthermore, progress in particle physics, aided by technologies like particle accelerators and detectors, helps us understand the fundamental forces and particles shaping the universe's behavior. Discoveries in this area could help us understand dark matter and dark energy, two crucial factors shaping the fate of the universe. For example, experiments at places like the Large Hadron Collider, LHC, might reveal new particles or phenomena that could change our view of the cosmos. Advancements in fields like quantum computing and nanotechnology also offer hope for cosmological research. Quantum computers, for instance, could tackle complex problems and analyze data in ways we can't do currently, potentially offering fresh insights into the quantum side of the universe and its eventual destiny. Supernovae are another fascinating aspect of studying the universe's end. These explosive events mark the finale of a star's life and are vital for understanding cosmic conclusions and the wider story of the universe. They aren't just visually spectacular, they're also treasure troves of information, helping astronomers unlock secrets of the cosmos, including hints about its eventual fate. When a star goes supernova, it shines brighter than entire galaxies for a brief period, emitting huge amounts of light and energy. This makes supernovae visible across vast distances, turning them into important markers in cosmic exploration. One of their significant roles is as standard candles. Certain types, like type Ia supernovae, always reach a consistent brightness at their peak, allowing astronomers to accurately measure their distance from Earth. By gauging the distance to these supernovae and their redshift, how fast they're moving away from us due to the universe's expansion, scientists can work out the rate of this expansion. This method led to a groundbreaking discovery that the universe's expansion is actually speeding up. This finding led to the theory of dark energy, a mysterious force propelling this acceleration. Studying supernova is like unlocking a cosmic treasure trove with profound implications for our understanding of the universe's destiny. These colossal explosions not only mark the dramatic end of stars, but also offer clues about the fate awaiting our cosmos. They shed light on the mysterious force known as dark energy, which holds the key to how the universe might end, whether it's in a big freeze, big rip, or another scenario. Additionally, supernovae have a crucial role in the cosmic recycling of matter. When they explode, they scatter heavy elements across space, which are vital for creating new stars, planets, and even the essential ingredients for life itself. In essence, supernovae symbolize both an end and a new beginning, echoing theories about the cyclical nature or ongoing evolution of the universe. Now let's talk about galactic collisions, these awe-inspiring events in the cosmos that actually contribute significantly to the universe's fate. Despite sounding tumultuous, these collisions are natural processes that shape the universe's journey. In the vastness of space, galaxies, held together by gravity, often encounter each other. These encounters range from gentle gravitational nudges to full-on mergers. When galaxies collide, it's not like a head-on collision on a road. Rather, they pass through each other due to the vast spaces between stars. Nevertheless, this cosmic dance has profound effects. One major consequence is the birth of new stars. As galaxies merge, their gas clouds collide and compress, sparking the formation of new stars in a spectacular display of cosmic creativity. This burst of star formation illuminates the merging galaxies and provides valuable insights into their life cycles and the processes driving star birth. Over incredibly long periods of time, galaxies collide with one another, which plays a vital role in their growth and development. The Milky Way, our own galaxy, has become as large as it is today, partly because it has merged with smaller galaxies in the past. This process is crucial for understanding what will happen to the universe in the far future. In a scenario known as the Big Freeze, where the universe keeps expanding forever, these collisions between galaxies might become rare as galaxies move farther away from each other. This could lead to a future where galaxies are isolated in a cold, expanding universe. These collisions also affect the way dark matter, a significant part of a galaxy's mass, is distributed. By studying these collisions, astronomers can gain insights into dark matter, which helps us understand the future evolution of the universe. One of the most anticipated galactic collisions in the distant future is between our Milky Way and the Andromeda galaxy, predicted to happen in about 4 billion years. This event will significantly change both galaxies, although it's not expected to directly affect any planetary systems, including our own solar system, because of the vast distances between stars. Instead, the merged galaxy, often humorously called Milkomeda or Andromeda Way, will mark a new chapter in the story of our local group of galaxies. Will studying exoplanets give us clues about the universe's end? The study of exoplanets, planets orbiting stars beyond our solar system, is a relatively new and quickly evolving area in astronomy. While exoplanets might initially seem distant and unrelated to questions about the universe's eventual fate, they actually provide valuable clues and insights into this cosmic puzzle. One significant way exoplanets contribute to our understanding of the universe's future is by shedding light on the formation and evolution of planetary systems. By observing a wide variety of exoplanetary systems, astronomers can gain a better grasp of how these systems develop over time. This knowledge deepens our understanding of how matter behaves and changes throughout the universe. For example, understanding the life cycle of planetary systems, from their formation to eventual demise, can offer parallels to the broader processes unfolding in the universe. Exoplanets also act as laboratories for studying the conditions that might lead to the end of planetary systems, which in turn informs our understanding of the ultimate fate of cosmic structures. For instance, studying exoplanets situated close to their stars and enduring extreme conditions provides insights into how planetary systems could be disrupted or destroyed. This research helps piece together a broader understanding of the stages leading to the end of both stellar and planetary systems across the universe. Moreover, exploring exoplanets enhances our comprehension of habitability and the potential for life elsewhere in the cosmos. Although not directly tied to the universe's ultimate end, this facet contributes to philosophical and scientific dialogues concerning the rarity of life and the evolution of the universe. It assists in framing our existence within a universe in constant flux and transformation. Additionally, studying exoplanetary atmospheres offers insights into the universe's destiny. By scrutinizing these atmospheres, astronomers discern their compositions and how they evolve over time under diverse cosmic influences. This understanding extends to how various cosmic conditions, such as radiation from nearby supernovae or the impacts of dark matter and dark energy, could shape planetary systems as the universe progresses. How does the large-scale structure of the universe affect its fate? The expansive structure of the universe, comprising galaxies, clusters, superclusters, and voids, profoundly impacts its destiny. This structure, molded by the distribution of matter and gravitational forces, isn't merely a static backdrop, but an active participant in the universe's ongoing evolution. A critical facet of this structure is its influence on the universe's expansion. Galaxies and cosmic structures are bound by gravity, influencing how they're distributed and move, thereby affecting the universe's growth dynamics. For instance, in densely packed regions like superclusters, gravitational forces can decelerate local expansion rates. Conversely, in vast cosmic voids with sparse galaxies, expansion proceeds relatively unhindered. The behavior of dark matter and dark energy, two enigmatic constituents of the universe, also significantly shapes the large-scale structure and consequently the universe's destiny. Dark matter, with its gravitational influence, aids in shaping and sustaining the cosmic web of galaxies and clusters. Meanwhile, dark energy propels the universe's accelerated expansion. The interaction between gravity and dark energy shapes how structures in the universe change and interact, which ultimately affects where the universe is headed in the long run. Additionally, the large-scale layout of the universe can help us understand its overall shape and structure, which is vital in predicting what might happen to it in the future. If the universe is closed, it could eventually stop expanding and start to collapse in on itself, leading to a potential scenario known as the Big Crunch. On the other hand, if it's open or flat, which is what current evidence suggests, it will likely keep expanding forever, possibly resulting in a big freeze or big rip. The way cosmic structures are spread out also has implications for how energy is distributed and how disorder, entropy, increases over time, which is crucial in theories like the heat death. As the universe changes over time, energy becomes more spread out across its vast expanse. The way the universe is structured affects how this spreading happens and how disorder increases over time, which is a big part of theories like the heat death. What role does string theory play in understanding how the universe will end? String theory, a field of physics that tries to bring together quantum mechanics and general relativity, offers a unique view on how the universe might end. It suggests that instead of tiny point-like particles, the fundamental building blocks of the universe are tiny vibrating strings. While string theory is quite complicated and mostly speculative, it introduces ideas that could change how we see the universe and its future. One fascinating idea in string theory is that there could be more than just the 3 dimensions of space and one of time that we're familiar with. These extra dimensions could have a big impact on how the universe evolves over time. For example, how these dimensions change over time might affect how fast the universe expands, or even the nature of dark energy. String theory also explores quantum gravity, which is a field aiming to describe gravity using the principles of quantum mechanics. Understanding quantum gravity is crucial for explaining phenomena such as black hole singularities or the conditions during the early universe. When considering the end of the universe, a better grasp of quantum gravity could offer insights into how the universe might behave as it keeps expanding, potentially uncovering new scenarios beyond those currently favored, like the Big Freeze or the Big Rip. Furthermore, string theory introduces the idea of multiple universes or a multiverse. This notion suggests that our universe might be just one of many, each possibly governed by different physical laws. If this aspect of string theory proves true, it could profoundly change our understanding of the universe's fate. Our universe's destiny might only be a part of a much larger and more complex multiverse, where each universe has its own distinct end. What are the signs that indicate the universe is moving towards its end? Detecting these signs involves a blend of intricate astronomical measurements and theoretical predictions. While the end of the universe is a far-off event projected to happen over an immensely long timescale, there are observable phenomena that offer clues about its eventual winding down. One significant sign is the rate at which the universe expands. Astronomers measure this expansion by observing the redshift of distant galaxies, how their light stretches to longer, redder wavelengths as they move away from us. This redshift confirms not only that the universe is expanding, but also helps scientists determine how fast this expansion is occurring. The discovery of the universe's accelerating expansion was a crucial moment in cosmology, indicating the influence of dark energy. If this acceleration persists, it supports scenarios like the Big Freeze, where the universe would continue expanding indefinitely, becoming colder and emptier over time. Another indicator is the life cycle of stars. Stars are like the universe's power plants, and by studying how they are born, live, and die, astronomers can learn a lot about what the universe might look like in the distant future. As the universe gets older, the rate at which new stars are formed is expected to slow down, and the stars that already exist will gradually run out of fuel. By looking at galaxies that are older and where star formation has slowed down a lot, we can get an idea of what might happen to our own galaxy billions of years from now. The behavior of galaxies themselves also gives us hints about the universe's future. In a universe that's heading towards a cold and isolated end, we'd expect to see galaxies moving away from each other more and more over time. This means that the rate of galaxies crashing into each other and merging would also slow down. Telescopes that are very powerful can observe these movements and interactions, providing data that fits into our long-term models of what might happen to the universe. Furthermore, the fate of the universe is connected to the way cosmic structures like black holes behave. According to theories like Hawking radiation, black holes should emit radiation very slowly, which means they would gradually evaporate over incredibly long periods. Studying black holes and their properties gives us insight into these far-off events. From black holes to light, how does the speed of light affect how we see the universe's end? The speed of light is crucial in how we observe and understand what might happen to the universe in the future. Light travels incredibly fast at about 299,792 kilometers per second, 186,282 miles per second. And this finite speed influences how we perceive the universe in important ways. The speed of light sets a boundary on how far we can see into the universe and, consequently, how much we can learn about its destiny. When we observe distant objects in space, we're essentially peering back in time. For instance, if we see a galaxy that's 1 million light-years away, we're seeing it as it was 1 million years ago because that's how long it took for the light from that galaxy to reach us. This concept, known as look-back time, allows astronomers to study how the universe has changed over time. By observing galaxies at different distances, we can construct a timeline of the universe's expansion and make predictions about its future. However, there's a limit to how far back we can look. The cosmic microwave background radiation, which is the afterglow of the Big Bang, is the oldest light we can detect, dating back to about 380,000 years after the universe began. Before this point, the universe was opaque to light, which means we can't directly see its earliest moments. This limitation also means there's a cap on our direct knowledge of the universe's future, since we can only infer what lies beyond based on our current understanding of physics. In terms of the universe's eventual end, the speed of light means that any observable changes, such as the accelerated expansion caused by dark energy, are seen with a delay. If the universe were heading towards a scenario like the Big Rip, where galaxies, stars, and even atoms are torn apart by the rapid expansion of space, we wouldn't witness these events until long after they've happened. The speed of light also affects our comprehension of events that might signal the universe's end. For example, if a distant galaxy were to vanish or alter suddenly due to some cosmic event linked to the universe's fate, we wouldn't become aware of it until the light from that event reaches us, potentially millions or billions of years later. How would the universe's end impact our understanding of time? The concept of time is intricately linked with our comprehension of the universe, and the way the cosmos eventually concludes would undoubtedly reshape our perception of time. In cosmology, time is often viewed as a linear progression, starting from the moment of the Big Bang and extending into the distant future. While our everyday experience of time is based on clocks and regular routines, the fate of the universe, as predicted by various cosmological models, can challenge and redefine our understanding of time in numerous ways. One fundamental aspect of time is its directionality, often called the arrow of time. This concept is linked to the increase of entropy or disorder in the universe, as described by the second law of thermodynamics. If the universe were to end in a scenario like the Big Freeze or heat death, where entropy reaches its maximum and everything becomes cold and uniform, the arrow of time would lose its meaning. Time would seem to stop because there would be no more change or dynamic processes. Einstein's theory of relativity brought about the idea of time dilation, which means time can pass at different rates depending on an observer's motion or gravitational field. In extreme situations like near black holes or in an expanding universe, time dilation can cause vastly different experiences of time for different observers. As the universe moves towards its end, these effects from relativity would become more noticeable. Quantum mechanics, the theory that governs the behavior of particles on a very small scale, introduces fascinating concepts regarding time. In certain quantum scenarios, time can act in a non-linear or even discontinuous way. If the universe's end involves quantum phenomena, it might challenge our traditional views of time. Some cosmological theories suggest that the universe might go through cycles of expansion and contraction, with each cycle starting with a new Big Bang. In such a cyclic model, time would persist through these cycles, suggesting a more cyclical and everlasting concept of time. In the end, whatever form the universe end takes, whether it's a freeze, a rip, a graceful fade into darkness, or something beyond our imagination, it prompts us to rethink our understanding of time. It could challenge our usual linear view of time and lead to new philosophical and scientific insights into temporal existence. The universe's end, in all its possible forms, urges us to reconsider our perception of reality. It invites us to reflect on the essence of time itself and the significance of our place within this cosmic narrative. The journey of discovery is ongoing, and the end of the universe is just one chapter in the grand story of the cosmos. As we continue to explore, learn, and dream, we are sure to encounter new marvels and uncover the mysteries of the universe, one documentary at a time. Thank you so much for watching SpaceDrift, and with that being said, take care. Contemplating the possibility of extraterrestrial life. What are the origins and historical context of the Fermi paradox? How does the Drake equation estimate the potential number of technologically advanced civilizations in our Milky Way galaxy? In what manner does the Kardashev scale classify extraterrestrial civilizations? What is the Great Silence? Where are the signs from aliens? These are just a few of the mysteries we're unraveling in today's documentary. Let's go on a journey to explore these questions through a comprehensive scientific lens. When did humans first begin contemplating the possibility of extraterrestrial life? In ancient Greece and Rome, early thinkers like Democritus and Epicurus pondered the vastness of the cosmos and speculated about the existence of other worlds. They believed that the universe was made up of countless tiny atoms which randomly collided to form diverse worlds beyond our own. Epicurus's follower,